From its vantage point a million miles away from Earth, a new telescope is quietly revising our understanding of the cosmos. Its observations have revealed phenomena that stretch the limits of theory. Galaxies that appear far too mature for their age, black holes that have grown impossibly large, and even a cosmic object hurtling through the void at 2 million miles an hour. This new perspective allows us to gaze toward the very edge of time, to see the first glimmer of light that brought an end to the universe's dark ages. We can now explore distant worlds where diamonds might fall like rain from carbon-rich skies, and are forced to confront findings so unusual that some scientists wonder if our entire model of reality is incomplete. In the cosmic twilight, a mere 290 million years after the Big Bang, something remarkable emerged. It was a galaxy, already fully formed, luminous, and chemically sophisticated. Researchers have since verified its existence with the most powerful observatory ever launched. This galaxy, named for a sacred river in the Himalayas, seems to violate nearly every established timeline for the early universe. To appreciate the full weight of this finding, it helps to consider what astronomers had anticipated. The standard model of cosmology offered a very specific narrative. Following the Big Bang, the universe was an intensely hot, chaotic plasma of fundamental particles. Over vast stretches of time, gravity would have slowly gathered this matter together. The very first galaxies, according to this model, should have been small, disorganized, and irregular collections of stars. It was thought to require billions of years for them to evolve into the grand, structured spirals we observe in the modern cosmos. Our own Milky Way galaxy, for instance, spent approximately 10 billion years developing its elegant, sweeping arms through a long history of collisions, mergers, and gradual ordering. This distant galaxy, however, achieved a similar state of organization in just a few 100 million years. When astronomers directed the James Webb Space Telescope toward a patch of the sky no larger than a grain of sand held at arm's length, they discovered something that, by all rights, should not have been there. The galaxy was found to contain material equivalent to 10 billion stellar masses. It had already arranged this vast quantity of matter into a well-defined disk. Furthermore, its chemical signature showed the presence of oxygen and other heavy elements, which can only be created through the life cycles of multiple stellar generations. What makes this observation so compelling is the origin of these heavier elements. In the beginning, they simply did not exist. The Big Bang produced only hydrogen, helium, and minute quantities of lithium. Every other element, from the carbon in our bodies to the oxygen we breathe, was forged in the hearts of stars and later dispersed into space when those stars exploded. For a galaxy to possess a significant amount of oxygen, entire generations of stars must have already lived and died. And yet, this particular galaxy was thriving when the universe was just 2% of its current age. The implications are profound. Either stars were able to form and perish at a rate far greater than we ever thought possible, or some part of our fundamental understanding of the early cosmos is incorrect. The scientists involved in this work have described the discovery as extraordinary. They dedicated 9 days of observation time to collect the necessary data. A total of 167 hours of imaging focused on a sliver of the sky so minuscule that a fractional change in the telescope's aim would have missed the object completely. It is worth reflecting on this fact. This galaxy was located by chance within a tiny, arbitrary sample of the cosmos. If such a mature structure can exist in one small field of view, it raises the question of how many more might be scattered across the sky. The statistical probability suggests that there could be many, a prospect that gives cosmologists pause. The team responsible for the finding was not seeking to overturn existing theories. They were engaged in a deep sky survey known as the James Webb Space Telescope Advanced Deep Extragalactic Survey. Their expectation was to find the primitive, chaotic beginnings of galaxies. Instead, what they saw was a structure that looked like a younger version of our own cosmic home. One member of the research team offered an analogy, suggesting it was like searching for a newborn infant, but finding a fully developed adult instead. The known physics of growth simply do not account for such rapid development, unless the physics itself is flawed. This is not speculation, it is confirmed science, published in peer-reviewed journals. The galaxy is real, its chemical makeup is verified, and it compels us to accept an unsettling truth. The universe was capable of assembling complex structures with a speed that no one had predicted. Matter somehow organized itself with astonishing efficiency in the cosmic dawn. Yet, the story of this galaxy is not an isolated event, and perhaps not even the most perplexing discovery to emerge from the telescope's early observations. Across the vast expanse of the early universe, appearing in image after image, astronomers began to see something even more puzzling. They noticed hundreds of tiny red points of light, objects so compact and so brilliant that no existing theory could readily explain them. When scientists finally determined what these objects likely were, it challenged everything we thought we knew about the formation of black holes. During the summer of 2022, the James Webb Space Telescope delivered its first scientific images to the world. Within just a few weeks, astronomers began to notice a recurring anomaly. Scattered throughout the data, present in nearly every deep field observation, were these small red dots of light. They were compact, unusually bright, and their nature was a complete mystery. Scientists gave them a straightforward name: little red dots. Initially, the leading hypothesis was that they were very distant galaxies. Older galaxies often appear red because their stellar populations have aged. As massive, hot, blue stars burn out, they leave behind cooler, longer-lived red stars, shifting the galaxy's overall color. This is a well-understood aspect of astrophysics. But there was a problem with this explanation. The objects were far too small. When astronomers attempted to resolve them and see the shapes of galaxies, they could not. The little red dots remained stubbornly point-like. They appeared to be less than 2% of the Milky Way's diameter. If they were indeed galaxies, their brightness would mean they were packed with an immense number of stars, which would need to be squeezed into an impossibly small volume. The night sky from a planet within such a galaxy would be overwhelmingly bright, with millions of stars visible to the naked eye. Such a high stellar density would contradict our understanding of how gravity organizes matter on galactic scales. The mystery, therefore, only deepened. If not galaxies, what were these objects? A new possibility soon came into focus. Perhaps the intense light was not from countless stars, but from a single, powerful source: a supermassive black hole. As black holes actively consume surrounding gas and dust, the material spiraling into them is compressed and heated to millions of degrees, releasing a tremendous amount of radiation that can outshine an entire host galaxy. This idea seemed more plausible, as it could explain the object's brightness without requiring an impossible density of stars. However, This solution introduced a new challenge. Actively feeding supermassive black holes of that magnitude should be powerful emitters of X-rays and radio waves. Astronomers began searching for these telltale signals. The initial results were profoundly puzzling, as scientists found almost nothing that made sense. These faint, little red dots seemed to defy every known classification. For ordinary galaxies, they were far too luminous. For typical active black holes, they were strangely quiet. They occupied an enigmatic space in between, a realm our cosmic models had no way to explain. And what was also striking was their sheer number. Hundreds of these objects have now been identified. Their presence is noted abundantly in observations of the early cosmos, in a period from around 400 million to 1 billion years after the Big Bang. Then, quite mysteriously, they appear to vanish entirely from the cosmic record. Whatever these celestial objects were, their existence was confined to a narrow window of cosmic history. They emerged suddenly, stayed visible for perhaps 500 million years, and then were gone. For a period of 3 years, astronomers engaged in a vigorous debate about their fundamental nature. Some researchers favored the hypothesis that they were galaxies heavily shrouded in dust. Others were insistent that they must harbor hidden black holes. The discussion became more heated as time went on. Competing theories began to multiply. But in the absence of better data, no one was able to prove their case conclusively. Then, in early 2025, a significant breakthrough was announced by researchers at the University of Copenhagen. Their team had spent 2 years analyzing the little red dots with the most detailed spectroscopic data ever obtained. What they concluded was startling. The little red dots are indeed young black holes, just not the type that anyone had anticipated. These black holes are enveloped within dense cocoons made of ionized gas. They are in the process of actively consuming that surrounding gas. This feeding frenzy generates an enormous amount of heat, which then radiates through the cocoon. The light, as it passes through this gaseous veil, acquires their characteristic red color. The cocoon also has another effect. It makes them appear vastly more massive than they truly are. The researchers determined that these black holes are approximately 100 times less massive than what earlier estimates had suggested. They are not the billion solar mass monsters once imagined. Instead, they are smaller, more voracious, and growing at a remarkable pace. This discovery resolves one major puzzle, but it immediately gives rise to another. If we are observing young black holes in the midst of a feeding frenzy, it is possible we are watching the birth of the supermassive black holes that now anchor every major galaxy. We could be seeing cosmic infants during their most crucial growth spurt. Yet, some scientists suspect the reality might be even more extraordinary. They propose that the little red dots may not be simple black holes at all. They could represent something that has never been observed before. What if these objects are not galaxies? What if they are not conventional black holes either? What if they are something entirely new to science? In late 2025, a team of researchers put forward a radical new idea. They suggested the mysterious red objects scattered across the primordial universe might constitute an entirely new class of cosmic structure. The name they gave them was black hole stars. The concept itself is as strange as it sounds. It asks us to imagine a black hole situated at the very center of a colossal sphere of hot, dense gas. The black hole is actively pulling this material inward with its immense gravity. As the gas plummets toward the event horizon, it accelerates to unbelievable speeds. The resulting compression creates temperatures reaching millions of degrees. This process liberates staggering quantities of energy. But a critical detail emerges here. Only a very small fraction of that infalling gas ever crosses the event horizon to disappear forever. The vast majority of it is blasted back outward. The intense radiation pressure pushes most of the material away from the black hole before it has a chance to be swallowed. Scientists sometimes use the analogy that black holes are messy eaters. They consume far less matter than they appear to grab. This rejected gas then forms a thick, turbulent atmosphere that surrounds the black hole. Viewed from a great distance, this entire structure, the black hole combined with its gaseous envelope, would look like a single, gigantic star. The difference is that it is not powered by nuclear fusion like ordinary stars. Instead, its engine is gravity itself, fueled by the violent compression of infalling material. One research team studied a particularly extreme little red dot that they nicknamed the cliff. Its spectrum revealed something without precedent. The object seemed to possess so much atmosphere that it could not be explained as a simple collection of stars. It looked more like one gigantic, very cold star. Its low temperature, however, was not due to a lack of energy. The perceived coldness was an effect of the gas envelope surrounding the central black hole. This dense cocoon absorbs the highest energy radiation from the core and re-emits it at longer wavelengths, which makes the object's surface appear red and relatively cool, even as a tremendous furnace rages within. If this interpretation proves to be correct, we may have discovered a missing link in the story of cosmic evolution. The reason this matters is profound. For a long time, astronomers have been puzzled by how supermassive black holes could grow so enormous so quickly. Normal feeding processes should require billions of years to achieve such sizes. Yet we find black holes of 1 billion solar masses existing when the universe was less than 1 billion years old. The timeline simply does not work with our current models. Black hole stars could potentially solve this problem. If a young black hole can wrap itself in a dense cocoon of gas, it can feed much faster than an exposed black hole can. The cocoon effectively shields the growing black hole from its own radiation, which would otherwise push away its fuel. This shielding allows it to consume material with much greater efficiency. The gas provides a constant source of fuel. The black hole grows steadily. Over several 100 million years, it has the potential to balloon from a modest seed into a true cosmic giant. This would also explain another perplexing observation. The little red dots are seen everywhere in the early universe, but they seem to vanish about 1 billion years after the Big Bang. If they represent a temporary phase of black hole growth, their disappearance makes perfect sense. The cocoon is eventually either consumed or blown away. The period of intense feeding comes to an end. What is left behind is a mature, supermassive black hole, sitting quietly at the center of a galaxy. We would never observe the black hole star phase in our modern universe because that stage of evolution concluded billions of years ago. The James Webb Space Telescope is essentially looking back in time, catching these objects during their brief but essential period of formation. It is important to remember that this remains a theory. Scientists are debating it with great intensity. More observations will be needed to confirm whether black hole stars are a real phenomenon. But the evidence so far is compelling. The spectral signatures, the apparent size, the brightness, and the timing of their appearance all seem to fit the model. If it is confirmed, this discovery would reshape our entire understanding of how galaxies form. The supermassive black holes at the heart of galaxies would no longer be seen as mere passengers that grew along with them. They would instead be recast as the foundational seeds from which the galaxies first assembled. But the strangeness uncovered in the early universe does not end there. Even when setting aside the little red dots, astronomers found something else that was deeply troubling. They found galaxies that are simply too big. The universe, it was believed, had a kind of speed limit for growth. When the James Webb Space Telescope started to survey the distant cosmos, it began to reveal galaxies that were far larger and more luminous than any model had ever predicted. These were not just subtle outliers. The discoveries presented a profound challenge, centered on galaxies that were between 10 and 100 times more massive than our understanding of physics would predict. To appreciate the scale of this crisis, it helps to review the accepted narrative of how galaxies are meant to come into being. In the aftermath of the Big Bang, the universe was a place of almost perfect smoothness. Matter was distributed with near total uniformity in every direction, but with infinitesimal imperfections. During the very first moments of existence, tiny quantum fluctuations introduced microscopic variations in density. Some areas of space contained just slightly more matter than their surroundings. Over vast stretches of time, gravity began to amplify these initial differences. The denser regions exerted a stronger pull, drawing in more and more material in a process of slow but relentless growth. Eventually, the first halos of dark matter took shape. Within these immense structures, gas began to pool. Stars started to ignite. The earliest galaxies were thus assembled, but it was a gradual affair that unfolded over hundreds of millions of years. The essential concept here is gradualness. The standard cosmological model provides a specific forecast for this rate of growth. There is a cosmic speed limit on how quickly matter can accumulate, a limit imposed by the fixed strength of gravity and the constant expansion of the universe, which works against gravity's inward pull. Based on these calculations, the first billion years of cosmic history should have only yielded small, dim, and disorganized structures. The appearance of anything as bright and orderly as our modern Milky Way should have been impossible until several billion years had passed. The James Webb Space Telescope, however, told a different story. In just its first year of operations, it found luminous galaxies scattered everywhere throughout the early universe. These were not merely a handful of strange anomalies, but a consistent population of objects that defied all expectations. Some of them shone with the brightness of mature galaxies, even though they existed when the cosmos was only 3% of its present age. The immediate response from the scientific community was one of disbelief. Many astronomers suspected an error in the measurements. It was thought that perhaps the telescope's sophisticated instruments required more precise calibration. Another possibility was that the distance calculations were flawed, mistakenly placing objects that were relatively close at profound cosmic distances. Research teams all over the world began to meticulously scrutinize the data. They recalibrated their tools and reanalyzed the findings. Yet the results remained firm. One especially striking case involved a galaxy observed at a high redshift, which meant we were seeing it as it was just 400 million years after the Big Bang. This galaxy already contained billions of stellar masses worth of stars. To put that into perspective, our own Milky Way galaxy holds approximately 200 billion stars, but it required more than 13 billion years to gather them. How could any galaxy accumulate such an enormous amount of material in such a short time? A number of explanations have been put forward. It is possible that the process of star formation was simply more efficient in the conditions of the early universe. Or perhaps the very first stars were far more massive and brilliant, causing young galaxies to seem brighter than their actual mass would indicate. Another idea is that dark matter may have behaved differently in those primordial times. But each of these potential solutions runs into its own set of problems. A higher efficiency of star formation would require physical conditions that we have not observed anywhere else. More massive primordial stars would have left behind distinct chemical signatures in the cosmos, signatures that have not been detected. And any modification to the behavior of dark matter would create conflicts with numerous other astronomical observations. Some scientists even began to wonder if these discoveries implied that the Big Bang occurred earlier than we currently believe. An older universe would naturally allow more time for cosmic structures to grow. But the cosmic microwave background radiation, the faint afterglow of the Big Bang itself, gives us an exceptionally precise measurement of the universe's age. The cosmos is 13.8 billion years old. This figure is considered non-negotiable. We are therefore confronted with a true scientific puzzle. The early universe was able to produce large, bright, and seemingly mature galaxies much faster than our models can account for. This means either some unknown mechanism accelerated their growth in ways we do not yet comprehend, or our fundamental models of the universe are missing a key component. This crisis of understanding does not end with galaxies. The very same observations that uncovered these impossibly large galaxies also brought to light something even more unsettling: supermassive black holes that completely dwarf their host galaxies. These are objects so disproportionately large that they violate a relationship between black holes and galaxies that astronomers had long considered to be universal. The established rules appear to be failing, and no one is certain why. Spiral galaxies, in particular, are understood to be ancient structures. The beautiful, swirling pinwheel patterns we admire in images of nearby galaxies are the product of billions of years of cosmic evolution. Our own Milky Way, for example, took approximately 10 billion years to form its graceful spiral arms. This formation is a process that demands time, stability, and a specific set of conditions. A galaxy must first accumulate a sufficient amount of mass. It then needs to settle into a stable, rotating disk. Within that disk, density waves must be able to propagate, compressing gas and igniting star formation along gently curving paths. Over immense cosmic timescales, the spiral pattern slowly emerges. This is considered established science, with dozens of complex simulations confirming this timeline. The creation of spiral structure requires cosmic patience. So, when astronomers discovered a fully formed spiral galaxy that existed just 1.5 billion years after the Big Bang, they were left searching for words. This galaxy is named Alaknanda, after a Himalayan river that is one of the two sources of the sacred Ganga River. The name was chosen for its deep cultural meaning. In Hindi, the name of the other source river, Mandakini, is also the word used for the Milky Way. What is so striking is that Alaknanda bears a shocking resemblance to our own cosmic home. It displays sweeping spiral arms, a well-defined disk, and vigorous star formation concentrated along the spiral pattern. These are all characteristics that astronomers associate with mature, highly evolved systems, not with a galaxy that existed when the universe was merely a tenth of its current age. This remarkable discovery was only possible because of a phenomenon known as gravitational lensing. A massive cluster of galaxies is positioned directly between Earth and Alaknanda. The immense gravity of this cluster bends and magnifies the light traveling from the more distant spiral, functioning as a natural cosmic magnifying glass. Without this powerful amplification, the galaxy would have been far too faint to be studied in such detail. By leveraging this magnified view, researchers were able to examine Alaknanda with an unprecedented level of clarity. They confirmed that its spiral arms were genuine features and not just an illusion created by distorted light. They carefully measured the rotation of its gas and stars. They calculated its total mass. The galaxy contains approximately 10 billion stellar masses. It managed to assemble and organize all of this material into a beautiful, stable spiral disk in only a few 100 million years. On a cosmic scale, this is an extraordinarily rapid pace of development. The research team that made the discovery described their findings with careful precision. They noted that the early universe was evidently capable of assembling galaxies far more quickly than anyone had ever anticipated. This galaxy had somehow managed to draw in enormous quantities of material and organize it into a stable structure almost instantaneously. But the question of how remains. One possibility centers on what are known as cold gas flows. If continuous streams of cold gas were able to funnel into the young galaxy without causing violent disruptions, it's conceivable that density waves could have established themselves very quickly. In this scenario, the galaxy would have had both the fuel for rapid star formation and the tranquil conditions necessary for spiral arms to develop. There is, however, another possibility, one that is more unsettling. It may be that spiral galaxies can assemble far more rapidly than our models have suggested. An alternative is that our simulations are somehow incomplete, missing a key element in the physics of how galaxies come into being. The galaxy known as Andanda is just one of several such discoveries. Using the James Webb Space Telescope, astronomers have identified a number of surprisingly well-ordered disk galaxies at profound cosmic distances. The continuous appearance of these objects presents a direct challenge to the long-held view that the earliest galaxies were exclusively chaotic and malformed structures. One particularly striking example, a massive spiral galaxy nicknamed the Big Wheel, was already in existence when the universe was less than 2 billion years old. Its form is so remarkably refined and structured that scientists had initially presumed it would be an elliptical galaxy, which is typically a more uniform collection of stars. What they found instead was a system with elegant, well-defined spiral arms, not unlike the galaxies found much closer to our own cosmic home. The implications of this are far-reaching. If entire galaxies could reach such a state of maturity so quickly, it raises the question of what other complex processes were unfolding in the young universe. The search for an answer leads to the very centers of these galactic structures. It points to objects that are even more perplexing and seemingly out of place than the galaxies that contain them. These are supermassive black holes, and they appear to have grown with astonishing speed. At the heart of almost every large galaxy, a truly colossal object resides. Supermassive black holes possess the mass of millions, or sometimes billions of suns. Their immense gravity serves as an anchor for the entire galactic structure. They can influence the birth of stars across thousands of light years of space. And during periods of active feeding, their luminosity can overwhelm that of all the surrounding stars combined. Within the local universe, these cosmic giants adhere to a clear and predictable rule. The mass of the central black hole is directly proportional to the mass of the galaxy that hosts it. Put simply, larger galaxies invariably contain larger black holes. This ratio has been observed to be incredibly stable. For every 1,000 units of mass contained in a galaxy's stars, its central black hole contains roughly 1 unit of mass. This consistent relationship has long suggested that galaxies and their central black holes grow in unison. They are thought to evolve together in a synchronized partnership across cosmic history. The laws of physics themselves seem to maintain this delicate equilibrium. If a black hole begins to grow too quickly, the intense radiation it emits heats the surrounding gas. This process effectively slows down the formation of new stars. Conversely, if stars begin to form too rapidly, they deplete the reservoir of gas that the black hole needs to accrete matter and grow. This intricate feedback loop was once considered a foundational and well-understood principle of galactic evolution. That understanding was upended when the James Webb Space Telescope turned its gaze toward the early cosmos. The observations it made did not just bend the established pattern, they shattered it entirely. In the most distant galaxies, supermassive black holes are exceptionally large for their size. They are, in fact, dramatically oversized. The familiar 1,000-to-1 ratio between the mass of a galaxy's stars and its black hole simply did not hold. Instead, astronomers discovered ratios closer to 100-to-1, and in some cases, even 10-to-1. In the most extreme instances, the mass of the central black hole was nearly equal to the combined mass of all the stars in its host galaxy. These are not minor deviations from the expected values. The black holes are 10 to 100 times more massive than the established relationship would ever predict. A dedicated team with researchers from Harvard and the Smithsonian conducted an analysis of 21 supermassive black holes. These objects were situated in galaxies seen as they were between 12 and 13 billion years ago. Every single black hole in their sample was found to violate the local scaling relationship. A thorough statistical review confirmed that this was not a measurement error or a collection of rare outliers. The black holes in the early universe are truly and fundamentally overmassive compared to their host galaxies. This finding presents a deep and fascinating puzzle for astrophysics. How was it possible for these black holes to accumulate so much mass while their surrounding galaxies remained so comparatively small? One potential answer lies in the sequence of events. It is possible that in the infant universe, black holes formed and grew first, with their host galaxies assembling around them at a later time. In this scenario, the black holes would have rapidly consumed the available primordial gas. This would have left little material for star formation, thus keeping the galaxies small as the black holes themselves expanded enormously. This idea, however, introduces its own set of challenging questions. Chief among them is the origin of the initial black hole seeds. The typical collapse of a massive star creates a black hole of only a few dozen solar masses. For such an object to grow to millions or billions of solar masses by accretion alone would require more time than was available in the early universe. To resolve this, some theorists have put forward the idea of direct collapse black holes. In this model, the first black holes did not begin as the remnants of stars at all. They would have formed when vast, pristine clouds of gas collapsed under their own gravity, forming a black hole directly. Such a process could create much heavier initial seeds, perhaps on the order of 100,000 solar masses. This would have given these early black holes a significant head start on their growth. The observations from the James Webb Telescope seem to lend support to this very theory. If black holes began with a much higher mass and grew more quickly than their galaxies, the imbalanced ratios seen in the data would be a natural consequence. Over the subsequent billions of years, the galaxies would have had time to grow and catch up. This would eventually establish the balanced relationship that we observe in the universe today. To confirm this hypothesis, however, astronomers need to find even smaller black holes at even earlier cosmic epochs. If these heavy seeds are a real phenomenon, a population of intermediate-sized objects should exist. They would represent the missing link between the theoretical primordial seeds and the giants already observed. The telescope's search continues, with every new observation probing deeper into the universe's past. Each new data set seems to reveal more of these black holes that, according to previous models, should not be able to exist. Among this growing collection of impossible objects, scientists eventually identified one that seemed to defy the most basic physical limits. It was a black hole that appeared to be consuming matter faster than the laws of physics should permit. There is a fundamental speed limit for any black hole. As gas and dust fall toward its event horizon, the material is compressed and becomes intensely hot. The resulting radiation creates a powerful outward pressure that pushes against the very material that is falling inward. At a certain point, this outward radiative pressure perfectly balances the inward pull of gravity. This critical threshold is known as the Eddington limit. A black hole cannot, in theory, accrete material beyond this point. Any excess matter would be blown away by the sheer intensity of the radiation produced by the meal it is already consuming. The black hole essentially becomes too bright to continue feeding. This limit is not a minor detail. It is a core concept derived from fundamental physics. It establishes a maximum possible rate for black hole growth. Even if a black hole feeds continuously at its Eddington limit, it still requires hundreds of millions of years to increase its mass in any substantial way. In November 2024, a team of astronomers announced a discovery that seemed to violate this principle in a spectacular fashion. Using the James Webb Space Telescope, they had studied a distant ancient galaxy already known to contain a powerful source of X-rays. This galaxy was observed as it was just 1.5 billion years after the Big Bang. At its center, a supermassive black hole was engaged in an extraordinary feeding event. The observational data showed powerful outflows of gas that were unlike anything previously seen. The velocity and sheer scale of these outflows strongly suggested the black hole was accreting matter at a rate more than 40 times its Eddington limit. This was not a small discrepancy. It represented a massive departure from what was thought to be physically possible. If the measurements were correct, this single, intense episode of feeding could account for the majority of the black hole's total observed mass. It implied that instead of growing slowly and steadily over eons, it might have acquired its immense size in a geological blink of an eye. The announcement was met with a mixture of great excitement and considerable skepticism throughout the scientific community. Some researchers believed it was proof of an entirely new mechanism for black hole accretion. Others, however, suspected a fundamental error in the interpretation of the measurements. By early 2025, a different group of scientists had reanalyzed the original data. Their work revealed that the initial measurements had been significantly affected by the presence of cosmic dust. Cosmic dust presents a fundamental challenge, acting as an interstellar veil that absorbs and scatters light across vast distances. This process has the effect of dimming the signals that eventually arrive at our telescopes. When astronomers fail to properly account for this dust, their conclusions can be significantly skewed. This can lead to a dramatic underestimation of a black hole's true mass, and it can also cause a misinterpretation of its feeding rate. Once the research team applied a correction for this dust extinction, the entire picture changed completely. The black hole, it turned out, was not consuming matter at an astonishing 40 times the Eddington limit. Its actual feeding rate was instead consistent with the accepted theoretical maximum. While this was still an impressive rate of accretion, it was no longer a finding that seemed to break the known laws of physics. This correction might sound like the end of the narrative, An extreme claim was investigated and found to be a measurement error, and one might assume the case is closed. However, the implications of this discovery reach much further. If obscuring dust could mislead astronomers in this specific instance, it raises a critical question. It suggests that dust could be misleading them in many other observations as well. Consider the newly identified class of objects known as little red dots. Each of these is known to be shrouded in a complex environment of dust. It is now plausible that their true properties are being systematically mismeasured. This uncertainty cuts both ways. Some black holes that we currently believe are impossibly massive might, in reality, be smaller. Conversely, others that appear to be feeding at a normal pace could be growing much faster than we currently realize. The lesson here is a humbling one. Even with the unparalleled power of the most advanced telescope ever constructed, interpreting signals from the early universe remains an extraordinarily difficult task. The combined effects of dust, immense distance, and the expansion of the cosmos all work to distort our view. This reality demands that scientists proceed with caution. Every extraordinary claim must be met with a demand for equally extraordinary verification. Yet, amidst these challenges of interpretation, one particular discovery from the James Webb Telescope needed no such correction. There was one object so dramatic, so undeniable in its nature, that its very existence served as a powerful validation. It confirmed 50 years of purely theoretical predictions. The object was a supermassive black hole, ejected entirely from its home galaxy. It is now racing through the void of space at a speed faster than almost any other object ever observed. An enormous object is tearing a path through the cosmos. It is a supermassive black hole, weighing 20 million times the mass of our own sun. It travels at an incredible 2.2 million miles per hour. In its wake, it leaves a trailing stream of newborn stars that stretches for 200,000 light-years. This may sound like a scene from science fiction, but it is a confirmed observation. The James Webb Space Telescope has furnished the definitive evidence that proves its existence. The first hint of something unusual came in 2023. Scientists were examining images captured by the Hubble Space Telescope when they noticed a curious thin line. This line seemed to extend from the center of a distant galaxy. The initial thought was that it might be an instrumental artifact, perhaps a glitch in the camera's sensor, or the result of a cosmic ray strike. However, the line persisted across multiple, separate observations. This confirmed it was a real feature of the cosmos, and it was unambiguously connected to the galaxy's core. Based on this, the team formulated a hypothesis. They proposed they were witnessing the wake of a runaway supermassive black hole. This would be a black hole violently ejected from its galaxy, plowing through the surrounding intergalactic gas. This passage would compress the material ahead of it, triggering a trail of star formation behind it. Skeptics, quite rightly, offered alternative explanations. It was suggested that the feature could be a shredded dwarf galaxy, or perhaps a galactic disk seen perfectly edge-on. The evidence from Hubble was compelling and suggestive, but it was not yet conclusive. It was then that the James Webb Space Telescope provided the final proof. Using its powerful near-infrared spectrograph, the telescope did something Hubble could not. It did not simply take an image of the object, it measured its motion. The spectrograph analyzed how fast the gas was moving at different points all along the linear structure. What it found removed any lingering doubt. Right at the very tip of the feature, there is an incredibly sharp change in velocity. The gas speed suddenly jumps by approximately 600 kilometers per second over a remarkably short distance of just 1 kiloparsec. This type of abrupt kinematic discontinuity can be caused by only one phenomenon: the signature of a supersonic bow shock. This means something truly massive is pushing through the gas faster than the speed at which sound waves can travel through that same medium. As it moves, it compresses the material in front of it, creating a powerful shock front. Behind this shock, the gas is able to cool down and collapse under its own gravity, triggering the formation of new stars. These newborn stars then stream out, creating the long, visible tail. The black hole itself, of course, remains invisible. By their very nature, black holes do not emit any light. But the profound effect it has on its surrounding environment effectively screams its presence across the cosmos. From this shock data, the researchers were able to calculate the black hole's velocity. Their measurement came to 954 kilometers per second, with a margin of error of about 100 kilometers per second. This is a speed of nearly 1,000 kilometers per second, which translates to roughly 2.2 million miles per hour. To put that into perspective, our own planet Earth orbits the Sun at about 67,000 miles per hour. This runaway black hole is therefore moving more than 30 times faster. At such a tremendous speed, the black hole will escape the gravitational pull of its galaxy entirely. It is destined to never return. It will wander through the vast emptiness of intergalactic space for all time. A true cosmic exile. A natural question arises from this. How can an object with the mass of 20 million suns be ejected from an entire galaxy? There are two known physical mechanisms that can produce such enormous velocities, and both scenarios involve events of extraordinary violence. The first possibility is a three-body interaction. This happens if three supermassive black holes find themselves in the same galactic core. Their complex gravitational dance can have a chaotic outcome, slingshotting one of the three members out at a tremendous speed. The other two black holes would remain behind, gravitationally bound to each other in a shrinking orbit. The second mechanism involves the power of gravitational waves. When two supermassive black holes merge, they release a colossal amount of energy in the form of ripples through space-time. If this merger happens to be asymmetric, the resulting burst of gravitational radiation can be directional. This can deliver a powerful kick to the newly formed larger black hole, giving it enough force to escape its galaxy. The team analyzing this particular runaway object believes the merger scenario is the most likely explanation. The measured mass and velocity of the black hole align well with predictions for a gravitational wave recoil kick. This remarkable discovery provides direct validation for 50 years of theoretical work. For decades, scientists had predicted the existence of runaway supermassive black holes based on their models. Now, finally, we have observed one directly. The galaxy that was left behind may now face a strange and unknown future. It is now a galaxy without a central supermassive black hole. We do not yet know what happens to a system like this over cosmic time, as we have never had the chance to observe one before. This runaway black hole did not simply appear from nowhere. Its origin story lies in a spectacular cosmic collision. It began with two galaxies crashing into one another. Their respective supermassive black holes would have then spiraled inexorably toward each other. The violent aftermath of their merger is what sent one of these monsters flying out into the void. The host system for this event has been given a fitting name, the Cosmic Owl. It earned this title because of its striking appearance. It looks like two ring galaxies that are in the process of approaching one another, their cores glowing brightly like a pair of luminous eyes. The overall shape is reminiscent of an owl's face, staring back at us across billions of light years. The cosmic owl system is located approximately 8.8 billion light years away from Earth. At such an immense distance, the light from this system has taken nearly 9 billion years to reach us. This means we are observing the system as it actually existed when the universe itself was less than 5 billion years old. Ring galaxies are, on their own, quite rare. They are typically formed when one galaxy punches directly through the center of another, sending ripples of star formation outward through the galactic disk, much like ripples from a rock dropped in a pond. To find two of these rare ring galaxies interacting with each other is an extraordinary sight. Yet the cosmic owl system contains something even more remarkable: that long, linear feature extending away from the galactic pair. This is the visible wake left behind by the runaway supermassive black hole. Astronomers believe the sequence of events that created this scene unfolded in a specific way. Long ago, there were two separate galaxies, and each of these galaxies harbored its own supermassive black hole at its center. It is plausible these galaxies also harbored additional black holes from even earlier mergers. Over millions of years, their mutual gravity drew them closer together in a slow cosmic dance. When galaxies collide, the vast emptiness of space ensures that individual stars rarely, if ever, strike one another. The supermassive black holes at the galactic centers, however, inevitably sink toward each other. Their orbits tighten as they lose energy, first through gravitational interactions with surrounding matter, and eventually through the radiation of gravitational waves. In the cosmic owl system, though, something seems to have disrupted this final stage. A powerful ejection event took place, and the primary explanations point to one of two scenarios. Either a complex three-body interaction flung one black hole outward, or two black holes merged in an asymmetrical way, creating a recoil kick that propelled the combined object away from its home. The ejected black hole carried an immense amount of momentum. It tore through the surrounding gas at supersonic speeds, compressing the material in front of it into a luminous bow shock. In its trail, this compressed gas began to cool and collapse, igniting the birth of new stars and creating a remarkable stream more than 60 kiloparsecs long. That distance, 60 kiloparsecs, translates to roughly 200,000 light years. For perspective, our entire Milky Way galaxy spans only about 100,000 light years across. The stellar wake trailing this runaway black hole is twice the diameter of our own galaxy. Observations from the James Webb Space Telescope captured this bow shock with unprecedented clarity. The spectrum of light from the region revealed the distinct signatures of fast radiative shocks and rapid cooling processes. Furthermore, measurements of the gas chemistry and velocity aligned perfectly with predictions for a supersonic object plowing through a diffuse medium. All the evidence points toward a single, extraordinary conclusion. A supermassive black hole was violently expelled from the cosmic owl and is now hurtling through intergalactic space, leaving a wake of creation behind it. This discovery carries profound implications. If runaway supermassive black holes are a real phenomenon, many more could be wandering the universe. Some projections suggest that millions of them might be silently drifting through the void between galaxies, remaining invisible and undetectable unless they happen to pass through gas clouds dense enough to generate some visible effect. The universe, it seems, may be populated by these cosmic exiles, enormous objects roaming the darkness. The cosmic owl also forces us to reconsider how supermassive black holes form to begin with. If they can be ejected, merged, and sent flying across the cosmos, Their life stories must be more violent and chaotic than we had previously imagined. To understand this violence, we must first understand how these objects are born, and the answer might lie with seeds far heavier than anyone anticipated. The question of the origin of supermassive black holes has been a persistent puzzle for astronomers for decades. We can see black holes containing billions of solar masses that sit at the hearts of galaxies, and we find them already existing when the universe was less than 1 billion years old. Yet, standard physics cannot explain how they grew so massive so quickly. The conventional way a black hole forms is through the death of a massive star. For example, a star perhaps 30 times the mass of our Sun will exhaust its nuclear fuel, collapse, and leave behind a black hole of maybe 10 to 30 solar masses. This process is well understood, but a starting point of 10 solar masses is insignificant compared to 1 billion. If you were to begin with a stellar mass black hole and feed it continuously at the maximum possible rate, it would still take billions of years to reach supermassive scales, which is longer than the universe had existed at the time we observed these ancient monsters. Clearly, something is missing from the narrative. Two principal theories have come to the forefront. The first suggests that early black holes experienced episodes of extreme feeding. It could be that the very first stars were giants, hundreds of times more massive than typical stars today, and thus left behind larger black holes when they died. Perhaps those initial black holes then merged over and over, combining their masses. Or perhaps feeding rates were occasionally able to exceed the accepted theoretical limits. This theory, however, depends on a special set of conditions, requiring a continuous supply of gas, few disruptions, and a great deal of time for this cumulative growth. The mathematics are challenging, but not impossible. The second theory puts forward a more dramatic origin story. What if the first black holes did not start small at all? What if they were simply born massive? This is the central idea of the heavy seeds theory. Instead of forming from the remnants of dead stars, these first black holes might have formed directly from the collapse of immense gas clouds. There would be no stellar phase, no gradual growth from a tiny beginning, but rather a direct gravitational implosion that could create a black hole 100,000 times more massive than our Sun in a single event. The conditions for such a direct collapse would have to be extreme. It would require an enormous cloud of gas that was relatively free of the heavy elements which would otherwise cause the gas to cool and fragment into smaller clumps. The cloud would also need to collapse uniformly, without forming stars along the way. Such conditions may have been present in the very early universe, before the first generations of stars had a chance to scatter heavy elements throughout the cosmos, leaving pristine gas clouds vulnerable to this kind of direct collapse. The James Webb Space Telescope has now delivered the first observational evidence that lends support to this heavy seeds model. A team from the Massachusetts Institute of Technology used the telescope's infrared instruments to study 6 ancient quasars, which are galaxies with actively feeding supermassive black holes. They were able to measure the light from the stars surrounding these black holes, something that was impossible with previous telescopes because the black hole's own glare would overwhelm everything else. The data revealed a crucial detail about these early systems. The black holes appear to have gained their mass before their host galaxies did. The stellar populations are younger and less developed than would be expected if the galaxies and their central black holes had grown up together. This finding supports the heavy seeds scenario. If a black hole began its life already enormous, with the galaxy assembling around it later, this is exactly the pattern one would expect to see. One researcher explained that in the early universe, it is possible that supermassive black holes acquired their mass before their host galaxies formed. These initial black hole seeds, he suggested, could have been more massive than anything we observe being created today. The implications of this are staggering. Supermassive black holes might not be mere passengers in the process of galactic evolution. They might be the very foundations upon which galaxies themselves are built. Still, the heavy seeds model remains theoretical. We have not yet directly observed one of these objects forming. The evidence is circumstantial, based on the properties of the systems we are able to see. To truly understand the birth of black holes, we need to peer even further back in time. We need to witness the universe's very first light. For hundreds of millions of years after the Big Bang, the universe was dark, and not just in the sense of empty space. In its earliest stages, the universe was an opaque realm, not because light was absent, but because it was unable to travel freely. The entirety of space was saturated with a dense fog of neutral hydrogen gas, which is exceptionally effective at absorbing most frequencies of high-energy light. Any photon attempting a journey across this primordial cosmos would have been almost instantly captured. This era is known as the Cosmic Dark Ages. During this time, there were no stars and no galaxies, only an immense, cooling expanse of elemental gas, waiting for a fundamental change. That change arrived with the ignition of the very first stars. The intense ultraviolet radiation they emitted began to ionize the hydrogen in their immediate vicinity, stripping electrons away from their atoms. This process created expanding pockets of transparent, ionized gas through which light could finally pass unimpeded. These clearings grew larger, spreading outward until they merged with other nearby bubbles of transparency. Gradually, this cosmic fog began to dissipate, and the universe underwent a profound transition from opaque to clear. This transformation is called the epoch of reionization. Determining when this process began, how it unfolded, and what sources drove it has been a primary objective of modern cosmology. For many decades, the prevailing scientific consensus was that reionization could not have started until the universe was approximately 500 million years old. The reasoning was that the first galaxies would have required a significant amount of time to form and then generate the vast quantities of radiation needed to have an effect. But then, the James Webb Space Telescope uncovered something that forced a revision of this entire timeline. It observed a galaxy named JADGS-Z13-1, which has a redshift corresponding to a time just 330 million years after the Big Bang. This is an exceptionally early period in cosmic history. What makes this galaxy truly extraordinary, however, is not simply its age, but its influence on its environment. When astronomers analyzed the light spectrum from this distant object, they discovered a signature they had not anticipated: a powerful emission line originating from ionized hydrogen. The signal was so pronounced that it had the brilliance of 10 billion stellar masses. Light of this kind should not have been detectable from such an early epoch. The neutral gas expected to envelop young galaxies should have completely absorbed it, unless that galaxy had already managed to clear out a large bubble of ionized space around itself. The data indicated that this was precisely the case. This small, ancient galaxy had already initiated the process of clearing the cosmic fog only 330 million years after the universe began. The scientists who found this described their work as observing the very start of reionization at a redshift of 13. No existing models had predicted that this could occur so soon. This discovery has profound and immediate implications. If reionization was underway earlier than previously thought, it follows that the first stars and galaxies must also have formed earlier. The established timeline of cosmic history requires adjustment. Still, many questions persist. The primary one is, what could be generating the radiation that ionized this bubble of space? The first generation of stars are theorized to be incredibly hot and to emit copious amounts of ultraviolet light. But there is another compelling possibility: supermassive black holes. As these immense objects consume surrounding gas, they release tremendous energy in the form of X-ray and ultraviolet radiation. A young, actively feeding black hole could ionize its surrounding gas just as effectively as millions of stars. It is plausible that the galaxy with the earliest known ionized bubble harbors one of the universe's first black holes, a possibility scientists are now actively investigating. Regardless of the source, this finding represents a major milestone. We have effectively captured the universe in the act of awakening. The long cosmic dark ages were drawing to a close, and light was beginning to prevail. The transition, however, was not a straightforward event. The reionization of the cosmos happened in ways far more intricate than anyone had foreseen. The epoch of reionization was not a singular occurrence, but a protracted process that played out over hundreds of millions of years and across billions of light years, varying significantly from one region to another. Some areas of the universe became illuminated early on, while others remained dark for much longer. The primordial fog did not recede uniformly. Instead, it cleared in a patchwork pattern, driven by localized radiation sources and shaped by the underlying distribution of matter and the random nature of structure formation. Mapping this complex, piecemeal transformation has been one of the most formidable challenges in cosmology. Until very recently, our ability to observe it was severely limited. The immense distances involved stretched the capabilities of every available telescope. The signals were incredibly faint, often absorbed or distorted by their journey through billions of years of an expanding universe. The arrival of the James Webb Space Telescope changed everything. Its unparalleled infrared sensitivity and high resolution allow it to peer deep into the epoch of reionization and witness the process as it happened. It can pinpoint the individual galaxies that contributed to the ionizing radiation and map the very boundaries between the cleared, ionized bubbles and the remaining neutral fog. The picture that is emerging from this data is one of both beauty and chaos. Reionization appears to have commenced much sooner than was once believed, perhaps around 300 million years after the Big Bang. Yet, it did not conclude until approximately 1.1 billion years after the Big Bang, which is over 200 million years later than previous estimates had suggested. This newly understood, extended timeline indicates that the transformation was a slow and uneven affair. Some galaxies were powerful enough to ionize their surroundings very quickly, while others were weaker and made only a minor impact. The neutral regions of gas between the bubbles were remarkably resilient, stubbornly resisting the advance of light. One of the most significant discoveries relates to the role of extremely faint dwarf galaxies. For many years, astronomers debated which types of sources were the primary drivers of reionization. Massive galaxies were the obvious candidates, as they produce enormous amounts of radiation. The issue is that there simply were not very many massive galaxies in the early universe. Dwarf galaxies, by contrast, were ubiquitous. Though small, dim, and individually weak, their sheer numbers were staggering. When scientists used the telescope to sum the cumulative radiation from all detectable dwarf galaxies, they made a startling finding. Together, these tiny galaxies produced enough ionizing photons to transform the entire universe. The team behind this discovery highlighted its profound significance, stating that ultra-faint galaxies were essential actors in the evolution of the early cosmos. They generated the radiation that converted neutral hydrogen into an ionized plasma. To understand cosmic history, it is now clear that we must understand these low-mass galaxies. This conclusion has consequences that extend beyond the study of reionization. If small galaxies dominated the early universe's photon budget, they must have also dominated star formation. It is possible that the vast majority of all stars that have ever existed were born inside galaxies too faint for us to see individually. The universe we can observe, the bright galaxies and dramatic cosmic structures, may only represent the visible portion of a much larger reality. Beneath this bright surface, countless tiny systems have been shaping the history of the cosmos since the very beginning. But the story of reionization is about more than just a tally of photons. The process itself had physical consequences that continue to resonate to this day. When a great wave of ionizing radiation moved through the early cosmos, it had a profound effect, warming the thin gas that filled the voids between galaxies. This heating process fundamentally changed the conditions under which matter could collapse and give rise to new structures. Small clouds of gas that might otherwise have become dwarf galaxies found themselves unable to hold together and were instead gently evaporated. Reionization was not merely an event that illuminated the universe. It was an act of cosmic sculpture. It set the rules for which structures could emerge and which could not, and we are still living with the results of that ancient transformation. The exact sequence of events, however, is something we are still working to understand. They are scattered across the primordial universe, almost entirely unseen. Most are too faint for our telescopes to register, and small enough that one could fit comfortably within a single spiral arm of our own Milky Way. These are the dwarf galaxies, the most unassuming members of the cosmic family. For many decades, astronomers tended to set them aside when considering the most fundamental questions. When they asked how the universe evolved, or what forces drove the great transitions in its history, their attention was drawn to the Titans. They focused on the massive galaxies containing billions of stars, or the brilliant quasars powered by supermassive black holes blazing from their cores. But the James Webb Space Telescope has brought a complex truth into focus. The giants were never the complete picture. It is even possible they were not the most critical part of the story. The telescope turned its gaze toward 8 of the faintest dwarf galaxies ever observed from the epoch of reionization. These tiny systems existed when the universe was in the midst of its change from darkness into light, approximately 900 million years after the Big Bang. What the observations revealed was that, despite their modest size, these galaxies were producing ionizing radiation at an astonishing pace. The combined power of their output was sufficient to explain a large portion of the photons required to fundamentally alter the state of the cosmos. And it is important to remember that these 8 galaxies represent a minuscule sample from a very small patch of the sky. When astronomers projected these findings across the entire population of dwarf galaxies throughout the observable universe, the implications were staggering. It now seems plausible that faint dwarf galaxies were responsible for producing the majority of the ionizing radiation during this critical era. They may have performed most of the labor in lifting the primordial haze. This discovery effectively inverts our long-held perspective on cosmic evolution. The very smallest structures appear to have had the most significant influence. In hindsight, the underlying physics is quite logical. The standard hierarchical model of structure formation predicts that dwarf galaxies would be the first to form. They are numerous because smaller clumps of matter collapse under gravity before larger ones can. And while their stellar populations are smaller, the stars they contain in the early universe can be exceptionally hot and bright. Massive galaxies, by contrast, come into being later on, built from the mergers of these smaller systems. By the time the giants begin to dominate the cosmic landscape, the process of reionization is already over. We were simply searching for the source of the light in the wrong place. Our focus had been on the most brilliant individual objects, causing us to miss the collective radiance of countless dimmer ones. The lesson here extends well beyond the field of astronomy. It suggests that sometimes the most profound changes arise not from a single dramatic event, but from the cumulative impact of innumerable small contributions. The universe often teaches us humility. But if dwarf galaxies were indeed the engines of reionization, we are presented with a new kind of challenge. These objects are exceptionally hard to investigate. Even an instrument as powerful as the James Webb Space Telescope can only resolve the most luminous among them. The faintest members of this vast population remain beyond our view, their characteristics inferred from models rather than directly observed. Future telescopes may bring us closer. With larger mirrors, more sensitive detectors, and extended observation periods, we might one day be able to see the smallest galaxies of the early universe. Until that time, we must continue our work with an incomplete data set. This discovery also prompts questions about the ultimate fate of these early dwarf galaxies. We can see what appear to be their descendants in our local cosmic neighborhood. They exist as small satellite galaxies in orbit around larger hosts, like the Milky Way. But the population numbers do not seem to align perfectly. It is possible that many of the early dwarfs were later destroyed, either absorbed by larger galaxies or undone by the very radiation they helped to create. The universe that these small galaxies brought into being may have ultimately worked against them. The same ionizing light that concluded the cosmic dark ages also heated the intergalactic gas, which prevented that gas from falling into the shallow gravitational wells of small galaxies. The dwarf galaxies that formed before reionization could continue to accrete matter and grow, but any that attempted to form afterward would have found their fuel supply had been shut off. Reionization was more than just a change in cosmic visibility. It was a fundamental shift in the conditions for building structures, and its effects continue to echo through billions of years of cosmic time. The expansion of the universe is a foundational concept in modern science. Since the 1920s, astronomers have understood that faraway galaxies are moving away from us. A clear relationship exists. The more distant a galaxy is, the more rapidly it recedes. This expansion is a stretching of space-time itself, carrying galaxies along with it, much like leaves floating on the surface of a river. The speed of this expansion is quantified by a value known as the Hubble constant. Pinpointing its exact value has been a central goal of modern cosmology, and it has also become one of the most persistent puzzles in all of physics. There are two primary techniques for measuring the Hubble constant. The first method relies on observing objects in the nearby universe. Astronomers look for stars that have a known intrinsic brightness. By measuring how bright these stars appear from Earth, they can accurately calculate their distance. When these distances are combined with measurements of their recession velocities, a local rate of cosmic expansion can be determined. The second method looks back to the very early universe by observing the cosmic microwave background, which is the faint afterglow of the Big Bang. This ancient radiation is imprinted with information about the conditions of the infant cosmos. By carefully analyzing its properties and using the standard model of cosmology, scientists can predict what the Hubble constant ought to be today. In principle, these two independent methods should yield the same result, but they do not. Measurements based on the nearby universe consistently arrive at an expansion rate of about 73 kilometers per second per megaparsec. The predictions derived from the cosmic microwave background, however, point to a value of around 67 kilometers per second per megaparsec. This difference may appear small, but it is substantially larger than the margins of error for the measurements. Both methods have been meticulously refined over many decades, yet the discrepancy remains. In fact, it has become slightly more pronounced as the precision of the measurements has improved. This persistent disagreement is known as the Hubble tension, and the James Webb Space Telescope has only deepened the mystery. There was a hope among some astronomers that the tension was the result of subtle measurement errors in the observations of the nearby universe. Previous instruments, most notably the Hubble Space Telescope, had difficulty resolving individual stars in very distant galaxies. It was theorized that the light from overlapping stars might be blending together, introducing a systematic error into the calculations. The James Webb Space Telescope is not susceptible to this particular problem. Its resolving power is significantly greater. It can cleanly distinguish individual stars that the Hubble telescope could not separate. When scientists re-examined cosmic distance measurements using data from the James Webb Space Telescope, they found that the earlier results were indeed correct. The expansion rate observed in the nearby universe holds firm at a value of around 73. The discrepancy, it seems, is not an error. This confirmation carries with it profound consequences, suggesting that something is flawed with our measurements of the cosmic microwave background, that our cosmological model is incomplete, or perhaps that both are true. For decades, the standard model of cosmology, known as lambda CDM, has served as a remarkably successful framework for explaining observations. It paints a picture of a universe dominated by dark energy and cold dark matter, all expanding according to Einstein's equations. This model aligns beautifully with the cosmic microwave background, yet it predicts a Hubble constant near 67. The universe simply appears to be expanding at a faster rate than this model permits. It appears something fundamental is absent from our understanding. Cosmologists have put forward a variety of potential solutions to this puzzle. It's possible the early universe held an extra component of energy that briefly accelerated its expansion. Perhaps dark energy operates in a way that differs from our assumptions, or maybe entirely new physics is needed to explain the observation. None of these ideas has achieved widespread acceptance, and so the tension continues without resolution. However, one particular idea consistently emerges in these discussions, a concept that could potentially explain both the expansion dilemma and the mystery of the unexpectedly bright early galaxies. This idea is known as early dark energy. What if two of the most significant puzzles in cosmology actually share the same underlying solution? The first of these puzzles is the Hubble tension, where the universe is expanding more rapidly than our standard model predicts. The second involves the primordial galaxies discovered by the James Webb Space Telescope, which appear too massive and luminous for how old they are. Standard models are unable to account for how they could have grown so large so quickly. These two issues seem to be entirely separate. One concerns the rate at which space itself is expanding, while the other relates to how structures form within that space. Distinct phenomena that should be governed by different physical laws. But a team of physicists from the Massachusetts Institute of Technology recognized a possible link. They put forth the idea that both anomalies might be explained by the presence of early dark energy. Dark energy is the term we use for whatever is causing the universe's expansion to accelerate today. In the standard model, this energy maintains a constant density throughout all of cosmic history. It is unchanging and does not engage with matter in any complex manner. But what if an additional temporary form of dark energy existed in the primeval universe? A component that was present only for the first few 100 million years before dissipating. This early dark energy would have driven the universe apart more forcefully during its infancy, stretching space more rapidly than the standard model assumes. Such an accelerated early expansion would produce several key effects. It would alter the equilibrium of cosmological parameters. The initial seeds of structure formation would be slightly larger, causing dark matter halos to grow faster. As a result, galaxies would form sooner and shine with greater intensity. To explore this hypothesis, the team employed sophisticated simulations. They integrated a model of early dark energy, one that had already been suggested to resolve the Hubble tension, and investigated its impact on galaxy formation. The outcome was remarkable. In the presence of early dark energy, the foundational structure of the early universe is altered in subtle yet significant ways. The amplitude of density fluctuations is enhanced, and dark matter halos grow to be larger. This leads to galaxies that form earlier and radiate more brightly. The model's predictions mirrored precisely what the James Webb Space Telescope had been observing. Massive, brilliant galaxies materializing much earlier than standard cosmology would ever allow. One researcher explained that their work showed the potential of early dark energy to act as a unified solution for two of cosmology's most significant challenges. If the observational data from the telescope continues to be validated, this could represent tangible evidence for its existence. It is an elegant proposal, where a single adjustment to our cosmological framework could resolve two distinct puzzles. This is often the way that physics advances, with unexplained phenomena accumulating until a deeper connecting principle is identified. But the concept of early dark energy remains controversial, and not all physicists are persuaded. Some contend that the evidence is merely circumstantial, while others note that this idea introduces new tensions with different sets of observations. The debate continues, and more data is required. The James Webb Space Telescope carries on with its observations, gathering evidence relevant to both sides of the argument. What seems to be growing clearer is that our map of the cosmos is incomplete. The standard model has been invaluable for decades, but it may now be encountering its limitations. The anomalies are accumulating more quickly than the explanations, and from the data, another mystery is beginning to surface, something even more peculiar than the Hubble tension. It seems dark energy itself might be changing over time. Dark energy was always thought to be a constant. The cosmological constant, first conceived by Einstein and later resurrected to account for the universe's accelerating expansion, was presumed to possess the same strength at all places and at all times, a fixed value woven into the very fabric of space. This assumption made the mathematics manageable and enabled cosmologists to construct predictive models that worked well for many years. New observations, however, suggest that dark energy might not be constant after all. Data gathered from multiple surveys, including the Dark Energy Spectroscopic Instrument, as well as analyses that incorporate findings from the James Webb Space Telescope, hint that dark energy has actually weakened over the last 4 to 5 billion years. If this proves to be true, the discovery would upend one of the core assumptions of modern cosmology. The evidence emerges from charting the universe's history of expansion with an unprecedented level of precision. By studying how galaxies cluster at various distances, astronomers can reconstruct how quickly space was expanding at different points in time. A curious pattern emerges from the results. The expansion rate in the distant past aligns reasonably well with predictions. But in the more recent universe, something appears to be different. The expansion is not accelerating as uniformly as a model with constant dark energy would suggest. One interpretation is that dark energy possessed greater strength in the past and has been steadily diminishing over time. The acceleration of the universe, in other words, is slowing down. The implications of this would be profound. If dark energy's influence continues to fade, the accelerating expansion could eventually cease, and the universe might simply coast to a halt. Or, depending on how this energy evolves, the expansion could even reverse itself. Some researchers even speculate about more extreme outcomes. A weakening dark energy could ultimately lead to a big crunch, an event where the entire universe collapses back in on itself. A different scenario envisions a big rip, where the decay of dark energy could fuel an accelerating expansion of such force that it would eventually pull apart galaxies, then stars, and finally the very atoms that constitute matter. These outcomes, of course, remain in the realm of speculation. Current data offer only faint suggestions of variation, not conclusive evidence, and significant uncertainties persist. More observations are clearly necessary. Yet, the simple prospect that dark energy might not be a constant marks a profound change in cosmological thought. For many decades, the prevailing view among physicists was of a universe with a fixed rate of acceleration, as if its accelerator pedal were locked in place. In this model, dark energy would perpetually drive expansion faster and faster, leading to a future of ultimate isolation. As galaxies drifted beyond one another's cosmic horizons into a permanent darkness, the fate of the cosmos seemed sealed. But a variable dark energy completely alters this narrative. The future suddenly becomes uncertain in ways it hadn't been before. The James Webb Space Telescope plays an indirect role in this unfolding story. Its findings of surprisingly mature galaxies in the very early universe present a challenge to timelines that are built on the assumption of constant dark energy. If dark energy were stronger or behaved differently in the primordial cosmos, it might account for some of these observed anomalies. What becomes clear is that everything is connected. The Hubble tension, the existence of massive early galaxies, and the idea of a variable dark energy are not isolated puzzles. Instead, they appear to be different facets of a single, more profound mystery concerning the fundamental nature of space, time, and energy. Cosmology now finds itself in a period of significant upheaval, as the certainties of the past begin to dissolve. It seems that new physics is waiting just beyond the limits of our current comprehension, and the telescope continues to find objects that, according to our models, should not be there. Sometimes, the universe conceals its most formidable objects in plain sight. A galaxy named Virgil, for instance, seemed entirely unremarkable when astronomers first studied it. Located in the early universe, approximately 800 million years after the Big Bang, it presented the image of a typical young galaxy, calmly forming new stars. Observations in ultraviolet and optical light revealed nothing out of the ordinary. It was the James Webb Space Telescope that ultimately uncovered its true identity. By using the mid-infrared instrument, researchers were able to peer deeper into the galaxy's emissions than was possible with any prior observatory. What they discovered transformed Virgil from a mundane object into something extraordinary. Concealed beneath its placid exterior was an active, supermassive black hole, a cosmic monster hidden behind thick veils of gas and dust. The optical light had shown only the galaxy's public facade, while the infrared light exposed its turbulent heart. The contrast was so stark that one researcher noted it was like observing two separate personalities. The galaxy's appearance in ultraviolet and optical light suggested a benign star-forming system. while its infrared signature pointed to something far more extreme. This finding carries consequences that extend far beyond this single galaxy. Surveys conducted by the James Webb Telescope often secure deep images using its near-infrared cameras, but only perform brief observations with the mid-infrared instruments. Achieving the same level of sensitivity at longer wavelengths requires significantly more observation time. This methodology suggests that astronomers could be systematically overlooking a hidden population of dust-obscured black holes, objects that appear normal at shorter wavelengths but conceal powerful engines at their centers. If Virgil is not an anomaly, and statistics suggest it likely is not, then the early universe may have hosted many more active black holes than current surveys indicate. These hidden giants could have been major players in cosmic history. It's possible they contributed to the process of reionization, flooding the early universe with ionizing radiation from behind their dusty shrouds. They might also explain some of the excess brightness observed in very distant galaxies. Furthermore, they could represent the missing link between the initial black hole seeds and the supermassive black holes we observe in the local universe today. The discovery also serves as a powerful demonstration of the importance of multi-wavelength observation. No single portion of the electromagnetic spectrum can provide the complete picture. The universe reveals itself differently in ultraviolet, visible, infrared, and radio light, with each window showcasing distinct phenomena. Before the James Webb Space Telescope, our view of the distant universe in infrared light was both narrow and indistinct. Now, that window is wide open, and what we are seeing is fundamentally reshaping our understanding of cosmic evolution. Virgil is situated at a pivotal moment in the timeline of the cosmos, when the universe was still emerging from its primordial fog. The first large-scale structures were just beginning to assemble, and black holes were growing at a rapid pace, consuming gas and shaping their environments. Understanding objects like Virgil is crucial for comprehending this transformative epoch. Each hidden black hole that we uncover adds another piece to the puzzle, and every seemingly ordinary galaxy that unveils an extraordinary secret deepens our knowledge. The universe, it seems, is filled with disguised monsters. They remain concealed by dust and immense distance, appearing harmless until the right instrument can finally unmask them. But Virgil's story is not the only surprise to emerge from the data. The most distant galaxy ever identified also contained secrets that challenged long-held assumptions about the chemistry of the early universe. The most remote galaxy ever found should have been, by all accounts, primitive. At a redshift of 14.3, we are observing this object as it was a mere 290 million years after the Big Bang. At that point in time, the universe was in its cosmic infancy. The very first stars had only recently ignited, and the first heavy elements were just starting to be synthesized. Scientists anticipated finding a chaotic, metal-poor system, a collection of hydrogen and helium with perhaps only trace amounts of heavier elements. They expected something raw and unfinished, fitting for the dawn of cosmic structure. What the James Webb Space Telescope found instead was oxygen. It detected significant quantities of it, enough to suggest that multiple generations of stars had already completed their life cycles within this ancient galaxy. This implies that star formation must have begun even earlier than anyone had thought possible. This discovery is one that requires careful consideration, as its implications are profound. Oxygen did not exist at the very beginning of time. The Big Bang produced only the lightest elements, with hydrogen accounting for about 75% of all primordial matter. Helium made up most of the remainder, and trace amounts of lithium filled out the cosmic inventory. Every other element, anything heavier than lithium, had to be forged in the nuclear furnaces of stars. As stars fuse hydrogen into helium, they release energy. They then fuse helium into carbon, releasing more energy still. This process continues, building progressively heavier elements until the star exhausts its nuclear fuel. The most massive stars conclude their lives in supernova explosions. These cataclysmic events disperse the heavy elements they created out into space, seeding the interstellar gas clouds from which the next generation of stars will form. Over the course of billions of years, this cycle of cosmic recycling enriches the universe with the full diversity of the periodic table. The presence of oxygen in the universe is tied to a specific cosmic process. It is forged in the hearts of massive stars and then distributed throughout space when those stars end their lives in supernova explosions. Discovering oxygen within a galaxy is therefore a clear indicator that generations of stars have already lived and died there. The galaxy observed at a redshift of 14.3 holds enough oxygen to suggest that substantial stellar processing has already taken place. This was far from a faint or marginal signal. The mid-infrared instrument on the telescope recorded distinct signatures of oxygen emission. The team responsible for this discovery dedicated an extraordinary amount of resources to the effort. They committed approximately 9 days of the telescope's time to this single target. This observation period included 167 hours of near-infrared imaging and 43 hours of mid-infrared imaging, all concentrated on a patch of the sky so minuscule it could be obscured by a single grain of sand held at arm's length. An element of fortune was also involved, as the galaxy was situated in the precise location needed to be seen by the mid-infrared instrument. A deviation of even a fraction of a degree in any direction would have meant it was missed entirely. What they discovered fundamentally challenges our timeline of cosmic chemical evolution. If this galaxy was already rich with oxygen just 290 million years after the Big Bang, it means the very first stars must have formed, lived out their lives, and perished even earlier. Current models propose that the first stars began to shine somewhere between 50 and 100 million years after the Big Bang. However, those were thought to be isolated phenomena, rare pioneers in a cosmos that was still mostly empty. The high concentration of oxygen in this distant galaxy points to a different scenario, where star formation was already widespread and robust. The universe, it seems, did not awaken slowly. It was racing toward maturity from its earliest moments. One scientist remarked that the finding was completely unexpected. The existence of such complex chemistry so early in the universe's history demands that models of galaxy formation be revised. Whatever physical mechanisms were responsible for building this galaxy operated at a pace far quicker than anyone had previously anticipated. But chemistry is not the only surprise the early universe holds. The telescope has also borne witness to violence on a cosmic scale, capturing the explosive death of a massive star in unprecedented detail from an epoch when such events were thought to be infrequent. On March 14, 2025, a pulse of high-energy radiation arrived at Earth, signaling the first supernova observed from the era of cosmic dawn. Its origin was impossibly far away, a gamma-ray burst, one of the most violent events known, that erupted when the cosmos was only 730 million years old. Gamma-ray bursts happen when massive stars die. These are not ordinary stellar deaths, but rather catastrophic collapses that result in the formation of black holes or neutron stars. The material falling inward unleashes a tremendous amount of energy, which is focused into narrow jets that tear through the dying star and blast into space. These phenomena are so brilliant they can be seen across the entire observable universe, serving as cosmic beacons that mark the final moments of the most massive stars. When astronomers registered this particular burst, they immediately understood its significance. The redshift pointed to an extreme distance, making this one of the earliest stellar deaths ever observed. Yet detecting the gamma-ray burst was just the beginning. The ultimate prize was to witness what followed, the supernova itself. Gamma-ray bursts are associated with a specific kind of supernova, sometimes called a hypernova or a broad-lined type 1c supernova. These explosions take place when huge stars that have already shed their outer layers of hydrogen collapse and detonate. The link between gamma-ray bursts and supernovae had been confirmed through observations in the local universe, but no one had ever verified this connection at such profound cosmic distances. The early universe was expected to be different. Its stars were born from pristine gas, and their deaths might have unfolded in unfamiliar ways. Some 110 days after the initial burst, the James Webb Space Telescope aimed at the location. Using its near-infrared camera, astronomers managed to separate the fading light of the explosion from the faint luminescence of its host galaxy. They confirmed the presence of a supernova. Its brightness and spectral qualities were a close match for supernovae linked to gamma-ray bursts in our own cosmic neighborhood. The underlying physics appeared to be identical. Massive stars in the early cosmos met their end in the same way massive stars do today. This confirmation carries deep implications. It signifies that the fundamental processes of stellar death were already established when the universe was merely 5% of its current age. The laws of physics did not require billions of years to settle into the familiar patterns we see now. They were consistent almost from the very beginning. One researcher involved called the discovery a smoking gun. The observation connects the deaths of massive stars to gamma-ray bursts across all of cosmic history. It shows that the entire cycle of stellar birth, life, and explosive death was fully operational at cosmic dawn. But the discovery also raises further questions. Supernovae scatter heavy elements into the cosmos, seeding future generations of stars with the materials necessary for planets and perhaps life to form. If supernovae were already happening frequently 730 million years after the Big Bang, the chemical enrichment of the universe was well underway. This ties back to the oxygen detected in that most distant of galaxies. The supernovae that spread that oxygen must have occurred even earlier. The first generations of stars were not just forming, they were already dying in spectacular fashion. The early universe was a violent place. Stars ignited with incredible speed, burned through their fuel in a few million years, and then exploded. Their deaths fertilized the cosmos, preparing it for the complex chemistry that would eventually give rise to planets, oceans, and life. Speaking of planets, the James Webb Space Telescope has unveiled worlds stranger than anything in our own cosmic vicinity, including one that might have diamond rain falling from skies of pure carbon. What happens when a planet orbits a dead star, and not just any stellar corpse, but a pulsar, a neutron star spinning dozens of times a second, sweeping beams of radiation across space like a cosmic lighthouse? This is an object with the mass of our sun compressed into a sphere the size of a city. The answer, as it turns out, was something no one could have predicted. The James Webb Space Telescope has discovered a planet unlike anything ever seen before. Its atmosphere defies all known mechanisms of formation. Its composition challenges our understanding of planetary science. And deep within its interior, it is possible that diamonds are forming continuously. The planet orbits a pulsar roughly 6,000 light-years away. It has a mass comparable to Jupiter, which makes it a gas giant by any standard. However, its atmosphere contains no water, no methane, and no carbon dioxide. None of the familiar molecules we find in gas giants throughout our galaxy. Instead, its atmosphere is dominated by helium and molecular carbon. Chemists have identified forms of pure carbon designated as C2 and C3. The existence of these molecules is exceptionally strange. This is because, at typical planetary temperatures, carbon has a strong tendency to bond with other elements. To find it in a pure state points to an environment profoundly different from any in our own solar system. One scientist noted that the discovery was an absolute surprise. The wider reaction among researchers was one of disbelief. The finding was radically different from what anyone had anticipated. This world is also strangely shaped. Powerful gravitational forces from the adjacent pulsar distort it into an oblong, lemon-like form. It completes an entire orbit in less than 8 hours. The planet moves at an incredible velocity as it circles its dead stellar host. Inside this world, the immense pressures could lead to astonishing transformations. Carbon, when subjected to extreme compression, will crystallize, and crystallized carbon is simply diamond. Researchers believe that carbon present in this planet's atmosphere might be descending into the interior. Within these depths, crushing forces would transform the carbon into diamond crystals. These resulting diamonds would then precipitate like rain, eventually collecting deep inside the planet. The idea of diamond rain is not entirely foreign to planetary science. It is a phenomenon that scientists have theorized could happen deep within Neptune and Uranus, right in our own cosmic neighborhood. This remote world, however, appears to take the concept to a whole new level. The puzzle only deepens when scientists attempt to explain this planet's origins. Planets typically coalesce from the disks of gas and dust that envelop young stars. They naturally assume the chemical makeup of the cloud from which they were born. Such clouds are usually rich in hydrogen, oxygen, nitrogen, and other prevalent elements. A world composed of pure carbon and helium could not have been created through this process. Planets orbiting pulsars are exceptionally rare to begin with. We know of only a small number. Their formation might occur from the leftover debris of the supernova that birthed the pulsar. Another possibility is that they form from material pulled away from a companion star. Yet, neither of these scenarios provides a straightforward explanation for the observed composition. A different explanation has been proposed, which centers on crystallization processes that are specific to cooling compact objects. Over billions of years, as the interior cooled, carbon and oxygen are thought to have separated. Crystals of pure carbon would have floated to the surface, mixing with the helium atmosphere. The oxygen and nitrogen, for some reason, remained behind. The physics behind this idea remains speculative. No one has a complete understanding of this world. What does seem apparent is that the diversity of planets extends well beyond what we have previously imagined. The universe constructs worlds we never thought possible. There are gas giants with diamond interiors. There are lemon-shaped worlds that speed around the corpses of stars. There are atmospheres of pure carbon beneath alien skies. But peculiar planets are not confined to exotic systems surrounding dead stars. The telescope has revealed strange worlds much nearer to us, one of which has held on to its atmosphere when it should have been scoured clean. Some planets are simply not supposed to have atmospheres. When a world orbits very close to its star, the powerful radiation should strip away any gases from its surface. The stellar wind acts to blast particles out into space. Ultraviolet light effectively shatters molecular bonds. Across millions of years, an atmosphere should evaporate entirely, leaving only bare rock. This is a well-understood principle of physics. It is a conclusion supported by countless observations. Small planets orbiting close to their stars are without air. Then, the James Webb Space Telescope turned its attention to a planet known as TOI 561b. This particular world orbits one of the most ancient stars in the Milky Way. The star itself formed approximately 10 billion years ago, at a time when the universe was not yet 4 billion years old. Any planets within this system have therefore weathered an unimaginable amount of time. TOI 561b is in such a close orbit that its year is shorter than 12 hours. At this proximity, the temperature on its day side climbs above 2,000 degrees. The surface itself is molten. A vast global ocean of magma covers the planet, glowing in shades of orange and red from the constant stellar bombardment. Based on all expectations, this world should be nothing but barren rock. 10 billion years of exposure to such intense radiation should have eroded any atmosphere long ago. The planet ought to be a burned-out cinder. Its primordial gases should be scattered throughout space. Yet, when astronomers took the planet's temperature, they found a discrepancy. The day side was not as hot as their models predicted.
Heat was being redistributed away from the hemisphere that directly faces the star.
Something was evidently transporting energy across the planet. The only viable explanation is the presence of an atmosphere. Subsequent analysis confirmed that a thick blanket of gases did indeed exist above the magma ocean. It was not a faint haze of vaporized rock, but a substantial atmosphere containing volatile compounds. This represents the most compelling evidence to date for an atmosphere on a rocky world outside our solar system. And it is thriving in a place where no atmosphere should be able to endure. A researcher characterized the planet as being much like a wet lava ball. The atmosphere somehow endures despite conditions that should have obliterated it. How could this be? The prevailing hypothesis suggests a process of constant replenishment. The ocean of magma is thought to be continuously releasing gases. Volcanic processes on a global scale are pumping volatiles into the atmosphere more quickly than the star's radiation can strip them away. This activity fosters a state of dynamic equilibrium. The atmosphere is simultaneously being destroyed and rebuilt. It persists in a condition of perpetual renewal. The implications of this discovery reach far beyond this one world. If oceans of magma can indeed maintain an atmosphere despite intense stellar radiation, the number of potentially compelling worlds grows significantly. Planets that we might have written off as airless could in fact possess thin yet meaningful gaseous envelopes. This is significant for the search for life. Atmospheres are crucial for regulating temperature. They provide a shield for surfaces against harmful radiation. They create an environment where complex chemistry can occur. A universe that contains more planets with atmospheres is a universe that holds more possibilities. TOI 561b, however, is not a habitable world. Its temperatures are far too high for life as we understand it. The interest in this case is purely scientific, not astrobiological. For clues of life, astronomers are looking to another world, one that has generated intense debate over what the telescope is truly capable of detecting. This is a planet where the potential for biosignatures has stirred controversy throughout the scientific community. Can the James Webb Space Telescope find evidence of life on distant planets? This question has been a point of division among astronomers since the telescope first became operational. The answer hinges not only on the instrument's technical abilities, but also on our definition of life and the certainty with which we can decipher chemical signs across interstellar space. In early 2025, a team of scientists made a stunning announcement. They reported finding what they described as the most powerful evidence yet for potential biosignature gases within the atmosphere of an exoplanet called K2-18b. This planet orbits a red dwarf star located about 124 light-years from Earth, falling into a class of worlds known as sub-Neptunes. The planet K2-18b has a size intermediate between that of Earth and Neptune. Worlds of this type have no direct counterpart within our own solar system, a fact that makes them exceptionally enigmatic objects of study. K2-18b orbits within its star's habitable zone, a region where surface temperatures could potentially permit the existence of liquid water. This has led some scientists to theorize that it might be a Hycean world, a distinct type of planet featuring a vast, globe-spanning ocean concealed beneath a dense atmosphere rich in hydrogen. Based on new transit spectra acquired by the James Webb Space Telescope, a research team reported the detection of chemical signatures that were consistent with dimethyl sulfide and possibly dimethyl disulfide. Here on Earth, the presence of these particular gases is overwhelmingly linked to biological activity in marine environments. They are produced in our planet's oceans by phytoplankton. The potential significance of this finding was profound. If these gases are indeed present on K2-18b, and if they cannot be generated through non-biological pathways, their existence could be an indicator of life. The announcement, however, was met with considerable skepticism from the broader scientific community. A number of other researchers contended that the signal was far too faint to support such a definitive conclusion. They pointed out that the underlying data contained a great deal of statistical noise. The detection itself was at the very threshold of the telescope's measurement capabilities. Furthermore, alternative explanations for the signal could not be confidently excluded. Critics also raised doubts about the Hycean world hypothesis itself. Some models suggested that K2-18b might not be an ocean-covered planet at all, but rather a gaseous mini-Neptune that lacks a solid surface. In such a scenario, any interpretation of atmospheric gases as a biosignature would be rendered meaningless. This ongoing debate effectively illuminates the boundaries of our current technological abilities. The James Webb Space Telescope was not originally engineered with the specific goal of analyzing exoplanet atmospheres. Its conception predated the modern explosion in the discovery of worlds beyond our solar system. Scientists are now pushing the instrument far beyond its initial design parameters, attempting to extract faint signals from the noise at the absolute edge of what is possible. Additional observations of the planet are already scheduled. Data from several more transits have been collected and are currently awaiting detailed analysis. This new information may ultimately resolve the question of whether dimethyl sulfide truly exists in the atmosphere of K2-18b. Yet, even if the detection is eventually confirmed, proving that it has a biological origin will be a challenge of immense difficulty. To make such a claim, we would need to show that no known abiotic process could create these gases, a monumental task given how little we understand about the chemistry of such exotic planetary environments. This is a standard of proof that may be impossible to meet with our current state of knowledge. Some astronomers, however, see inherent value in this controversy, irrespective of the final outcome. One perspective holds that if the public learns to approach future claims of life detection with greater caution, it would be a positive development.
Science, after all, is a process that fundamentally requires skepticism. K2-18b will continue to be a target of high scientific value for understanding the atmospheres of sub-Neptunes. Whether or not it harbors life, the study of its chemistry provides invaluable lessons about planetary diversity and the vast range of conditions that can exist throughout our galaxy. The search for life goes on. With each new observation, we move incrementally closer to resolving the most ancient question humanity has ever posed. Are we alone? But before that question can be answered, we must first comprehend the diverse environments where life might have a chance to emerge. And the very early universe presented its own set of surprises, pushing the known limits of what stars can be. What did the very first stars actually look like? This question has captivated astronomers for many decades. The initial generation of stars, which are referred to as population 3 stars, coalesced from pristine gas composed almost entirely of hydrogen and helium. These primordial clouds lacked the heavy elements that help modern nebulae cool efficiently, and as a result, they collapsed to form objects of enormous mass. Current theories predict that these stars were true giants, possibly hundreds of times more massive than the typical stars we see today. These primordial titans would have burned with incredible heat and luminosity, bathing the young universe in a flood of intense ultraviolet radiation. They would have lived their lives quickly and died young, ending in spectacular supernova explosions that seeded the cosmos with the first generation of heavy elements. The challenge, however, is that no one has ever directly observed a population 3 star. They existed too early in cosmic history, for too brief a time, and at too great a distance. By the time their ancient light finally reaches our telescopes, they have long since vanished. The closest we can come is to identify environments that approximate those primordial conditions. This means searching for galaxies with exceptionally low concentrations of metals, where the process of star formation might still follow these ancient patterns. The James Webb Space Telescope has now located such a place. A galaxy designated Excels 63107 is situated at a redshift that tells us we are seeing it as it was less than 600 million years after the Big Bang. It is remarkably small, measuring less than 200 light-years from one side to the other. For a sense of scale, our own Milky Way galaxy spans about 100,000 light-years. But what makes this distant galaxy so extraordinary is its chemical composition. It contains a mere 1.6% of the oxygen found in our own star. This represents one of the lowest metallicity levels ever measured for any galaxy at any cosmic distance, and its stars appear unusual. The light spectrum reveals signatures that do not align well with standard stellar models. The levels of ionization within the galaxy are exceptionally high. The radiation being emitted is unusually intense. Something within this system is generating a tremendous quantity of energetic photons. One possible interpretation is that this galaxy possesses what is known as a top-heavy initial mass function. This would mean that massive stars are forming in far greater numbers than would normally be expected. Instead of a typical distribution of stellar masses, this ancient system appears heavily skewed toward the formation of giants. If this is true, it carries enormous implications for our understanding of the era of reionization. Massive stars produce significantly more ionizing radiation per unit of mass than smaller stars do. A universe in which the first galaxies had top-heavy mass functions would have completed its reionization much more rapidly than one with normal stellar populations.
There is another possibility, one that is perhaps even more exciting. It could be that the conditions within Excel's 63,107 are so similar to those of the primordial universe that it is hosting stars that closely resemble population 3 objects. While not the true first generation, which would have zero metals, they would be something very close, offering a precious window into what the earliest stellar populations might have been like. The galaxy is forming stars at a prodigious rate for its diminutive size, creating roughly 8 times the mass of our star every year, all concentrated within a volume smaller than most modern star clusters. The sheer intensity of this activity is what produces the unusual blue light that was detected in the telescope's images.
Scientists are careful to emphasize that more observations are required. These interpretations are still preliminary, but the discovery itself demonstrates that extremely primitive galaxies did exist during the period of cosmic dawn, and that our new telescopes have the power to study them in remarkable detail. We are now approaching the very boundary of first light, peering back toward the emergence of the first structures from the cosmic darkness. Each metal-poor galaxy we find brings us closer to understanding how the universe made the transition from its state of primordial simplicity to the complex, enriched cosmos we observe today. But not all of the earliest galaxies were actively building stars. Some appear to have ceased their star formation prematurely, and their early dormancy presents another puzzle for cosmology. Galaxies are generally thought to evolve over long timescales. The Standard Model suggests a familiar progression. Young galaxies form stars with great vigor as gas flows in, collapses under gravity, and ignites. Over immense cosmic timescales, a galaxy's supply of gas is meant to slowly dwindle. As the fuel runs out, the birth of new stars declines, and eventually, the galaxy settles into a quiet state of existence. The result is a red and dead system, populated exclusively by aging stars. This entire process is expected to unfold across many billions of years. A galaxy that forms in the young universe should therefore continue its active star-making for a very long time before its reserves are exhausted. The James Webb Space Telescope, however, has uncovered galaxies that seem to have broken this fundamental rule. Astronomers peering deep into the early cosmos at a time less than 2 billion years after the Big Bang discovered galaxies that had already stopped forming stars. They were quiescent, effectively dormant.
An analysis of their stellar populations revealed that star formation had actually ceased hundreds of millions of years prior. According to our models, these galaxies simply should not have been there. Scientists gave them a fitting nickname: sleeping beauties. These are systems that entered a state of cosmic slumber far sooner than any prediction allowed. Their very presence challenges our core understanding of how galaxies grow and change over time. The puzzle they present has 2 distinct parts. First, for these galaxies to be quiescent so early, they must have produced their stars with extraordinary speed. They would have needed to generate their entire stellar mass within the first billion years of the universe's existence, an absolutely astonishing rate of star formation. Second, some powerful force must have then abruptly switched that process off. The supply of gas had to be cut, and the question is, how? Whether it was consumed, violently expelled, or removed by another mechanism, the essential fuel for starbirth had vanished. Several potential explanations have been put forward by researchers. One possibility involves active galactic nuclei. If the supermassive black hole at a galaxy's heart becomes intensely active, its powerful radiation can heat the surrounding gas, preventing it from cooling and collapsing to form stars. In this scenario, the black hole's sheer energetic output effectively sterilizes its host galaxy. Another idea is that galaxy mergers could be responsible. When galaxies collide, the ensuing chaos can ignite furious bursts of star formation that rapidly burn through all the available gas. The merged remnant is then left depleted and quiet. Environmental factors might also have a role to play. Galaxies residing in very dense cosmic neighborhoods face different pressures than those in isolation.
Gas can be stripped away from them through interactions with nearby structures, yet none of these explanations can fully account for the population of galaxies being observed. The sleeping beauties are too massive, too numerous, and appeared too early for any one of these mechanisms to be the sole answer. This discovery adds to a growing body of evidence that the early universe was a far more dynamic place than our standard models have predicted. It seems galaxies formed more quickly. They evolved more quickly. They reached final stages that should have required billions of additional years to achieve. Something appears to have accelerated the pace of cosmic evolution. The cause remains unknown, whether it was an early form of dark energy, different properties of dark matter, or perhaps some fundamental physics we have yet to grasp. The universe transitioned from its primordial state to something resembling the modern cosmos with unexpected haste.
These sleeping beauties are a key symptom of this accelerated timeline. They serve as powerful proof that galaxy evolution was already remarkably advanced when the universe was merely a fraction of its present age. And they are not the only indication of this premature cosmic maturity. Spiral galaxies, those iconic symbols of cosmic order, have also been found far too soon. Spiral galaxies represent the crown jewels of cosmic structure. Their majestic sweeping arms, their elegant symmetry, and their orderly rotation are the product of billions of years of gravitational choreography. They are mature systems, the result of long-term evolution in stable conditions. Our own galaxy, the Milky Way, is a spiral. From our vantage point inside it, we see its structure as a luminous band stretching across the night sky. That band is the galactic disk seen edge-on, a plane filled with hundreds of billions of stars arranged into graceful spiral patterns.
Forging such an intricate structure takes an immense amount of time. Dark matter must first gather into massive halos. Gas must then cool and settle into rotating disks. Density waves have to propagate through these disks, triggering star formation along gracefully curved paths. The entire sequence was assumed to unfold over many billions of years. At least, that was the prevailing assumption. In early 2025, the James Webb Space Telescope delivered a finding that directly challenged this picture. It revealed a massive spiral galaxy, nicknamed the Big Wheel, that existed within the first 2 billion years of the universe. A galaxy of its mass at that epoch should have been elliptical. The expectation was that massive early galaxies would be smooth, disorganized blobs of stars, their structures not yet settled into disks and arms. The violent mergers thought to be common in the early universe should have disrupted any attempt to form a spiral. But the Big Wheel displays a clear spiral structure. Its arms are well defined, and its rotation is orderly. It has the appearance of a galaxy from our local universe, not one from the cosmic dawn. One researcher described the finding as remarkable, noting that having such a beautiful spiral form implies that the processes that built it must have been very neat. Either the expected violent mergers did not happen, or the majority of its mass formed in place without suffering major disruptions. This discovery is part of a growing catalog of unexpectedly mature structures in the early cosmos. There is the spiral galaxy Alaknanda, the numerous disk galaxies identified at high redshift, and the sleeping beauties, with their ancient stellar populations. A distinct pattern is emerging from these observations. The early universe was not the chaotic, primitive environment we had long envisioned.
It was capable of producing organized, sophisticated structures much sooner than our models predicted. This finding challenges fundamental aspects of cosmological theory. The hierarchical model of structure formation, for instance, posits that small objects form first and then merge over time to create larger ones. In this view, smooth, organized structures should be late arrivals, the products of extended, peaceful evolution. The observations, however, seem to show the opposite. Some of the largest, most organized structures appeared very early, beating the predicted timeline by billions of years. The implications of this are vast, rippling through nearly every field of astronomy. Models of galaxy formation will need to be revised. Simulations of dark matter may require new parameters. The basic narrative we tell about cosmic evolution is in need of an update. Some scientists propose that an early form of dark energy could explain the accelerated formation of these structures. Others are looking into the possibility of modified dark matter properties. Still others wonder if we are missing a piece of fundamental physics. At present, no consensus has been reached. The scientific debate is active and ongoing. Each new observation from the James Webb Space Telescope adds another layer of evidence and complexity to the picture. What seems increasingly clear is that our view of the universe has been incomplete. The telescope has not just been filling in the details of an established framework. It has revealed that the entire framework itself may need to be reconsidered. And so we are left with what is perhaps the most unsettling conclusion of all, that everything we thought we knew is now being questioned. The fundamental story of the cosmos, how galaxies and black holes came to be, the essence of dark energy, and the speed of universal expansion, is being rewritten. The cosmological models that have guided astronomy for generations are struggling to account for the reality observed by the most powerful telescope ever launched. This is not a matter of small corrections. It represents a profound reassessment of our place in the universe. We need only look at what the James Webb Space Telescope has uncovered in its first few years. It has seen galaxies that appear too soon after the Big Bang, already too massive and well-organized. It has found spiral structures that should have taken billions of additional years to form. There are dormant systems that ceased creating stars when the cosmos was in its infancy. The telescope has also revealed black holes that are far too large for the galaxies they inhabit, and some that are consuming matter at rates previously thought impossible. In one stunning observation, it captured a runaway supermassive black hole hurtling through space at 2 million miles per hour, providing dramatic validation for a theory that had stood for 50 years. Countless little red dots, once a mystery in images of the early cosmos, are now understood to be nascent black holes shrouded in dense cocoons of gas. This may even represent an entirely new celestial class known as black hole stars, the very seeds of the colossal entities that anchor every major galaxy today. The epoch of reionization, a transformative period in cosmic history, appears to have begun earlier than we thought. Faint dwarf galaxies, it turns in, generated sufficient radiation to alter the entire universe. The very first bubbles of ionized gas emerged just 330 million years after the beginning of everything. Meanwhile, the Hubble tension has been both confirmed and intensified, showing that the universe is expanding more rapidly than our most trusted model can predict. Dark energy itself might be weakening over time, a possibility that casts the ultimate destiny of the cosmos into doubt. Even on the scale of exoplanets, expectations are being defied.
We have seen lava worlds with atmospheres that should not be able to exist, and lemon-shaped planets orbiting dead stars where it may rain diamonds. The detection of potential biosignatures has ignited passionate debate over our ability to identify life from light years away. Any one of these discoveries would be a landmark achievement. Viewed together, they amount to a scientific revolution. This is precisely how science makes progress. New observations put established theories to the test. Those theories are then revised or discarded entirely. Our understanding grows deeper, and the cycle repeats. Yet this particular moment feels different. The anomalies are not isolated incidents. They emerge everywhere the telescope directs its gaze.
From early galaxies and black holes to cosmic expansion rates and dark energy, the challenges cut across multiple disciplines. They all point toward a missing piece in our fundamental picture of reality. Some scientists propose that a concept called early dark energy could resolve several of these puzzles at once. Others suggest that our theories of dark matter require modification. A few even wonder if general relativity itself needs to be adjusted on the vastest of scales. For now, no one has the answer. The data continues to stream in as the James Webb Space Telescope carries on with its observations, adding new pieces to the puzzle. Future observatories will undoubtedly expand upon these findings, probing even further back into cosmic time. What we can state with certainty is that the universe is far stranger and more dynamic than we ever conceived. It evolved more quickly, and it built complex structures with greater efficiency. It contains objects and hosts phenomena that humble our most elegant theories. This realization should be a source of excitement, not discouragement. The most profound moments in science arrive when observation outpaces explanation, when nature shows itself to be richer than our models allowed. It is in these moments, when we must go back to first principles and rethink everything, that true progress is made. We are living in such a time. A telescope 1,000,000 miles from Earth has shattered our comfortable assumptions. The cosmos is not what we thought it was. But we now know which questions we need to ask. We know where the deepest mysteries are hidden. We have clues that point toward more fundamental truths. The great journey of discovery goes on, and whatever we find next will surely be stranger still. Certain images come to define an entire era. In 1995, the Hubble Space Telescope produced a photograph that would become one of the most iconic scientific images in history. It showed immense columns of gas and dust, illuminated from behind by the light of newborn stars, rising like celestial spires from the darkness of space. They were named the Pillars of Creation. For nearly 3 decades, this image shaped the way humanity pictured the birth of stars. It was reproduced in countless textbooks, and museum visitors would stand mesmerized before giant prints. The pillars became a symbol for the wonder of cosmic exploration. Then, the James Webb Space Telescope looked again, and its vision transformed our understanding of what truly happens inside those famous structures. The pillars are located within the Eagle Nebula, approximately 6,500 light-years from our planet. Each column is several light-years in height. To appreciate this scale, consider that the distance from our Sun to its nearest stellar neighbor is just over 4 light-years. These are formations of almost unimaginable size. Hubble revealed their majestic beauty, but Webb has shown us their underlying violence. Using near-infrared light, the telescope penetrated the opaque, dusty exteriors that had long concealed the pillars' inner workings. For the first time, astronomers could peer deep inside the columns. What they saw was a scene of pure chaos. There were hundreds of newborn stars,
launching fiery jets outward at supersonic velocities. Shock waves were visibly rippling through the surrounding gas. The pillars are not the tranquil nurseries they once appeared to be. They are turbulent arenas where gravity battles against radiation as new stars violently claw their way into existence. One team of researchers analyzing the Webb data identified 253 candidates for young stellar objects inside the pillars. These are protostars, still in the process of accumulating mass from their environment. Some are only a few 100,000 years old, mere infants in cosmic terms.
The most revealing detail, however, was where these infant stars were located. They were concentrated along the edges of the pillars, not scattered randomly throughout. Furthermore, their ages seemed to get younger with increasing distance from the massive stars that illuminate the nebula. This distinct pattern tells a compelling story of creation born from destruction. The powerful radiation from nearby mature stars is actively sculpting the pillars, eroding them much like wind carves sandstone in a desert. At the same time, as this radiation compresses the gas along the pillar's edges, it triggers gravitational collapse. The pillars are being destroyed, and their very destruction is what gives rise to new stars. This mechanism, known as triggered star formation, had been theorized for decades, but had never been observed with such clarity. The Webb data show the process unfolding in real time. The rate of star formation within the pillars has risen sharply over the last million years, precisely in step with the intensifying erosion. The wavy, glowing patterns that trace the pillar's edges are not simply decorative. They are the supersonic jets erupting from newborn stars and slamming into the ambient gas. Each of these collisions generates bow shocks, which are rippling patterns of heated material that map the violence of stellar birth. The scene was described by one researcher as practically pulsing with activity. These nascent stars, perhaps only a few 100,000 years old, signal their birth with displays of spectacular energy. Yet, within this visual splendor lies a story of impermanence. The very same radiation that triggers the formation of new suns is also the force that dooms the pillars themselves. In time, these immense columns will be completely worn away by stellar winds and light. Their constituent gas is destined to disperse back into the void of space. The stars that were born from them will eventually drift apart from one another. The pillars of creation are ultimately transient structures, cosmic monuments to a fleeting moment in the universe's evolution. In what may be 100,000 years, they will have vanished entirely. We are simply fortunate to exist in a time when we can witness them still standing. And while our instruments study stellar nurseries in our own galaxy, the telescope has also directed its gaze toward mysteries much nearer to home. This includes the most distant planet in our solar system, a world where light behaves in ways that no one had anticipated. For 30 years, astronomers conducted a patient search. They had strong reason to believe auroras should exist on Neptune. Every other gas giant in our system displays them. Jupiter's auroras, for instance, burn with an intensity hundreds of times greater than those on Earth. Saturn is adorned with luminous halos that cap its poles. Even far-off Uranus shimmers with faint northern and southern lights. Neptune, however, held its secrets close. When the Voyager 2 spacecraft flew past the ice giant in 1989, its instruments picked up faint suggestions of auroral activity. The technology of that period, however, could not confirm or properly characterize what was occurring in Neptune's upper atmosphere. In the decades that followed, ground-based telescopes continued the search. The Keck Observatory in Hawaii aimed its enormous mirrors at the remote planet. The Very Large Telescope in Chile scanned its atmosphere in the infrared spectrum. Still, nothing definitive was found. The fundamental challenge was the sheer distance involved. Neptune orbits our star at a separation 30 times greater than Earth's. Across such a vast expanse, the delicate glow of an aurora is exceptionally difficult to distinguish from the profound blackness of space. Then, the James Webb Space Telescope had its opportunity to look. In June of 2023, a team of astronomers pointed the telescope's near-infrared spectrograph at Neptune. Their original objective was to analyze the planet's atmospheric circulation patterns. Instead, what they discovered left them astonished. Clear and unmistakable auroras, appearing as glowing cyan patches of light high in Neptune's atmosphere. This marked the first confirmed detection of auroral activity on the solar system's most distant major planet. One scientist, who had devoted years to this very search, later conveyed a sense of awe at the detail and clarity of the signal. After decades of unsuccessful attempts, the discovery was made almost incidentally during observations planned for entirely different scientific goals. The auroras themselves, however, immediately raised new questions. On our own planet, auroras tend to gather around the magnetic poles. Charged particles from our sun spiral down along magnetic field lines, striking the upper atmosphere near the Arctic and Antarctic regions. These collisions excite atmospheric gases, which then release energy as the shimmering curtains of green and red light we recognize as the northern and southern lights. Neptune's auroras, by contrast, appear nowhere near its poles. They instead manifest at mid-latitudes, in regions that would be equivalent to South America or Southern Africa on Earth. This unusual placement is a direct consequence of Neptune's uniquely tilted magnetic field, which is offset from the planet's rotational axis by a remarkable 47 degrees. The reason for this severe misalignment of Neptune's magnetic field remains a mystery. The planet itself rotates on an axis tilted just 28 degrees from the vertical, a figure nearly identical to Earth's own axial tilt. Its magnetic field, however, points in a completely different direction, as if the planet's rotational and magnetic orientations are entirely independent of one another. The Webb observations also uncovered a crucial chemical fingerprint. For the very first time at Neptune, astronomers detected the trihydrogen cation, a molecule with the designation H3+. This particular ion is formed when charged particles collide with hydrogen-rich atmospheres, making it a definitive indicator of auroral processes. Scientists had previously identified the trihydrogen cation in the atmospheres of Jupiter, Saturn, and Uranus. Its presence at Neptune was therefore expected, but it had never been verified until Webb's observation. Perhaps the most puzzling information emerged from the temperature data. Neptune's upper atmosphere has cooled significantly since the Voyager 2 flyby, registering several hundred degrees colder than the measurements taken back in 1989. This dramatic cooling might be the very reason the auroras remained concealed for so long. Colder temperatures correspond to fewer energetic particles, which in turn produce fainter emissions and signals that were simply buried below the detection limits of every instrument that had tried before Webb. But the question remains as to why Neptune has cooled so profoundly. The planet is situated so far from our star that its seasonal changes unfold over many decades. Its weather patterns may shift on timescales that are longer than a human career. Astronomers now intend to observe Neptune over the course of an entire solar cycle. This 11-year study may reveal how this distant world responds to the changing conditions that flow outward from our sun. It seems that every answer the telescope provides only serves to generate a new set of questions. Even closer to home, within the expanding debris of a dead star, Webb has unveiled structures that no one had ever anticipated. 340 years ago, a star in our galaxy exploded. The light from this cataclysmic event reached Earth sometime during the late 1600s. Although no contemporary observers documented anything unusual in the sky, the supernova's light was likely absorbed by dense dust clouds within the Milky Way before it could be seen by observers on Earth. Today, we know this expanding shell of stellar remains as Cassiopeia A. Located 11,000 light-years away, it is the youngest known supernova remnant in our galaxy. The James Webb Space Telescope has since transformed this object into a laboratory for studying how massive stars end their lives. Previous observations from other telescopes had depicted Cassiopeia A as a generally circular bubble of hot gas, glowing brightly in X-rays and radio waves. The Hubble telescope revealed its intricate knots and filaments in visible light. But Webb's vision in the infrared spectrum uncovered something entirely new. Deep within the remnant, seen in silhouette against its interior, is a structure that had never been observed before. It appears as a thick sheet of material marked by dozens of small, almost perfectly circular holes. Due to its coloration in the representative color images, astronomers have nicknamed it the Green Monster. This discovery was completely unforeseen. Supernova remnants are expected to be hollow shells, representing the outer layers of an exploded star expanding outward into space. From our vantage point, the Green Monster is situated in front of the primary shell, almost like a veil draped across the cosmic wreckage. This raises immediate questions about what it is and how the holes within it were formed. Detailed analysis suggests that the Green Monster is composed of circumstellar material. This is material the star shed before its demise, now lit and shaped by the subsequent shockwave. What stands out are the apparent holes, which seem to have been punctured into the structure. The cause appears to be dense knots of stellar debris, fragments of the original star traveling outward at thousands of kilometers per second. These powerful projectiles have torn clean through the surrounding sheet of material. The science team cataloged more than 24 of these circular voids. Each one measures between roughly 1 and 3 arcseconds on the sky. To put this in perspective, if our own sun were at the center of such a void, the feature's edge would extend to the inner boundary of our solar system's Oort cloud. These are immense structures. Yet Webb's findings at Cassiopeia A continued beyond the so-called Green Monster. The observatory also uncovered a delicate web-like system of unshocked ejecta filaments. This is matter from the exploded star that has not yet collided with anything to disrupt its journey. These ethereal threads hold clues about the star's final moments. They preserve a record of the turbulent mixing that took place as the core collapsed and the outer layers were violently cast into space. Webb also registered an unusually bright emission from carbon monoxide. While this molecule is known to form in the cooling remnants of a supernova, it had never been seen at such elevated temperatures. This discovery suggests that carbon monoxide is being both formed and destroyed in a continuous cycle. It is a portrait of chemistry happening in real time within the chaotic aftermath of a star's death. The sheer volume of information was so profound that one scientist remarked they could spend an entire career working to decipher it all. These images simply contained far more detail than anyone had foreseen. Perhaps the most fascinating discovery was what astronomers refer to as baby Cassiopeia A. This is a small, faint patch of light, a light echo located 170 light-years behind the primary remnant. Photons from the initial explosion are the source of its illumination, having finally reached a distant cloud of dust and warmed it enough to become visible. Light echoes provide a unique way for astronomers to observe ancient phenomena as if they were occurring today. The echo from baby Cassiopeia A carries information about the explosion itself, data that has been journeying across space for centuries. Supernovae have a direct and personal relevance to us all. They are responsible for creating the heavy elements that constitute our own bodies. The calcium in our bones, the iron in our blood, and the oxygen we breathe were all forged inside exploding stars. These elements were then scattered across the cosmos in events just like the one that produced Cassiopeia A. To understand how stars die is to understand the story of our own origins. And as scientists examine the remnants of these dead stars, they are also able to witness the birth of new ones. In the intricate dance of planet formation, the telescope has observed something truly remarkable. The story of our own cosmic neighborhood began 4.5 billion years ago, when an enormous cloud of gas and dust collapsed under its own gravity. A young star ignited at its core, surrounded by a swirling disk of leftover material. This disk contained the raw ingredients that would one day form planets, moons, asteroids, and comets. We refer to this kind of structure as a protoplanetary disk. The James Webb Space Telescope is now revealing these cosmic construction zones with unprecedented clarity. One of its most well-known subjects is HL Tauri, a young star situated about 460 light-years from Earth in the Taurus star-forming region. Earlier observations with the Atacama Large Millimeter Array had shown concentric rings and gaps within the disk around this infant star, hinting that planets might already be carving out their orbits. When Webb pointed its infrared instruments at HL Tauri, scientists anticipated seeing the disk in more detail, or perhaps even detecting the forming planets themselves. What the telescope observed instead was entirely unexpected, leaving the research team astonished. It revealed streams of matter flowing from the star's larger, surrounding envelope of gas down into the protoplanetary disk. Much like rivers feeding a lake, these streamers transport raw material from the vast cloud into the very region where planets are being built. One researcher explained that they were seeing a highly complex and dynamic system. Material was flowing from the outer envelope toward the inner parts of the disk where planets were assembling. This process, known as infall, had long been theorized but had never been witnessed with such directness. The images from Webb show it unfolding in the present moment. It is possible our own solar system was fed in precisely this manner during its infancy. But HL Tauri is just one example. Webb has studied a number of protoplanetary disk systems, and each one has revealed its own unique features. Around the star MWC 758, previous observations had identified spiral arms forming within its disk. Such patterns suggest that a massive planet is orbiting somewhere inside, its gravity stirring the material like a spoon in soup. Webb's observations have now placed the tightest constraints to date on where this suspected planet could be hiding. While the data did not directly reveal any new planets, the level of sensitivity achieved is a significant breakthrough. Each non-detection helps to narrow down the possibilities, informing astronomers about what kinds of planets can and cannot exist in these environments. In another major finding, Webb confirmed a long-held theory of planet formation by observing water vapor in protoplanetary disks. The model proposed that pebbles coated in ice drift from the cold, outer regions of a disk toward the warmer, inner areas. When these pebbles cross the frost line, the point where temperatures are high enough for ice to turn into vapor, they release their water. Webb detected this exact chemical signature in compact disks around young stars. These observations serve as the first direct proof of pebble drift, a fundamental process that could explain how rocky worlds like Earth gather their mass. The telescope also found that protoplanetary disks in the early universe survive for longer than they do in the present day. In metal-poor environments, which resemble conditions from billions of years ago, disks around young stars seem to persist for extended periods. This additional time would have provided a greater opportunity for planets to form, potentially accounting for some of the surprisingly mature structures Webb has seen in ancient galaxies. The most surprising discovery, however, may have been what Webb found around brown dwarfs. These are objects too small to ignite as stars, but too massive to be considered planets. Within the Orion Nebula, the telescope confirmed that 20 of these so-called failed stars have their own protoplanetary disks. This finding implies that planets might be able to form even around the universe's smallest and dimmest stellar objects. The capacity for world building across the cosmos is far greater than anyone had previously imagined. Each new observation teaches us something more about how these cosmic neighborhoods come together. Every disk is a laboratory for planet formation, and every streamer is another clue. And on occasion, the telescope manages to see the finished product directly, capturing the image of an actual planet for the very first time. 3 years into its mission, the moment astronomers had been waiting for arrived. On June 25, 2025, it was announced that the James Webb Space Telescope had secured its first exoplanet discovery. The profound nature of this achievement lay in its method. It was not accomplished by observing a star's light fade as a world passed in front of it, nor by detecting the subtle gravitational tugs a planet imparts on its star. Instead, Webb had managed to see the world itself, a faint glow of infrared light shining in the vast darkness. This planet, designated TWWA-7b, circles a youthful star 111 light-years from Earth, marking a significant milestone in the telescope's scientific journey. Capturing a direct image of a world beyond our solar system is a task of extraordinary difficulty. The fundamental challenge is that stars are millions of times more luminous than the planets that orbit them. This overwhelming stellar brightness completely washes out the delicate light from any nearby planet. The effort to discern an exoplanet next to its host star has often been likened to trying to spot a firefly hovering beside a searchlight from many miles away. Webb was able to overcome this immense obstacle by employing a coronagraph, a specialized instrument designed to block the direct light from a star, much like our moon obscures the sun during a total eclipse. Once the star's intense glare was suppressed, faint objects in its vicinity could finally emerge from the surrounding darkness. The Discovery team, guided by researchers from the French National Center for Scientific Research, had concentrated their search on young stars encircled by debris disks that were oriented face-on from our perspective on Earth. This particular alignment gives astronomers a clear view of the entire disk structure, rather than just a thin sliver of its edge. The star known as TWWA-7, which also goes by the name CE Antliae, was a perfect candidate that met these criteria. Earlier observations of this system had already uncovered 3 separate rings within its debris disk, with noticeable gaps that suggested unseen planets were gravitationally sculpting the material. In June 2024, when Webb focused its gaze on the slender middle ring, it registered a faint source of infrared light. After meticulously ruling out any instrumental errors and verifying that the detection was genuine, the team reached the conclusion that they had found a planet. The world, TWWA-7b, has a mass roughly equivalent to that of Saturn. This detail is particularly noteworthy as it makes the planet 10 times less massive than any exoplanet that had been previously captured through direct imaging. The discovery serves as a powerful demonstration of Webb's ability to perceive worlds significantly smaller than the colossal gas giants imaged by earlier observatories. This finding was further solidified by computer simulations. When the research team modeled the presence of a Saturn-mass planet at the exact location of the detection, the resulting simulations perfectly reproduced the thin ring and gap structure that had been observed in the debris disk. It was clear that the planet's gravity was shaping its local environment in precisely predictable ways. The world itself is very young, estimated to be only a few million years old. Because planets that have recently formed are still intensely hot from the residual energy of their creation, they radiate more brightly in infrared light compared to older, cooler worlds. It was this specific thermal signature that Webb was able to detect. One researcher involved in the study described the discovery as likely being just the beginning of what the telescope could achieve. Webb possesses the potential to image even smaller planets in the years to come, perhaps even worlds with as little as 10% of Jupiter's mass. This capability is opening entirely new frontiers in astronomy. Before Webb, direct imaging techniques were limited to spotting only extremely massive, hot planets that orbited very far from their stars. Now, the telescope can investigate smaller planets at closer distances, bringing science nearer to the range where rocky worlds might one day become visible. The finding also underscores how planets can influence debris disks in observable ways. By carefully studying how these disks react to a planet's gravitational pull, astronomers can infer the existence of worlds that are too faint to be seen directly. TWWA-7b will certainly not be the last of its kind. The telescope is continuously examining other young stellar systems, seeking out the faint embers of newly formed worlds. Every new discovery enriches our census of planetary systems and illuminates the incredible diversity of outcomes that can arise when gas and dust collapse around infant stars. Yet, while Webb identifies new worlds around distant suns, it may have also found one much closer to us. This is the intriguing case of a planet that appeared and then vanished near our closest stellar neighbor, a mere 4 light-years away. That is the distance to Alpha Centauri, the nearest star system to our own. In cosmic terms, it is practically in our backyard. A journey there, at the speed of light, would take just 4 years, though with our fastest current spacecraft, the trip would last for tens of thousands of years. Still, the destination remains conceivable. For decades, astronomers have been searching for planets around these neighboring stars. 3 worlds have been confirmed to orbit Proxima Centauri, the system's faint red dwarf. However, Alpha Centauri A and B, the 2 bright, sun-like stars that form a binary pair, had long resisted any planetary detection. That changed in August of 2024, thanks to the James Webb Space Telescope. By using its mid-infrared instrument paired with a coronagraph to mask the starlight, astronomers picked up a faint object near Alpha Centauri A, a signal more than 10,000 times fainter than the star itself. The initial excitement was immense. If this object proved to be a planet, it would be the closest one to Earth found orbiting within the habitable zone of a star similar to our Sun. While it was a gas giant, it could potentially host moons where liquid water might exist. But then, the planet disappeared. Follow-up observations conducted in February and April of 2025 revealed nothing. The telescope was pointed at the same spot, using the same methods, but saw no trace of the object it had detected just months before. Scientists were faced with what one researcher called the case of a disappearing planet. The mystery, they reported, prompted astronomers to immediately turn to their computers. They ran millions of simulations of potential orbits, incorporating every available piece of data, including ground-based observations that went as far back as 2019. The solution they uncovered was both elegant and frustrating. In half of the stable orbital configurations that fit all the observations,
The planet would have been positioned too close to its star to be seen during the follow-up attempts. It was not necessarily absent from the system, but rather concealed within the star's brilliant glare. Based on the brightness of the original detection and the orbital constraints, researchers believe the object is a gas giant with a mass similar to Saturn. It appears to follow an elliptical path around Alpha Centauri A, a path that carries it to a distance between 1 and 2 times that of Earth's orbit around our Sun. This particular orbit places the planet squarely within Alpha Centauri A's habitable zone, the region where temperatures could potentially permit liquid water to exist on a solid surface. As a gas giant, the planet itself could not harbor life as we understand it, but any moons it might possess are another matter entirely. The discovery, should it be confirmed, would represent the closest directly imaged exoplanet, the coldest and oldest world ever captured in such a portrait, and the nearest planet found in the habitable zone of a sun-like star. Confirmation, however, will require patience. If the models are correct, the planet's orbit should bring it back into a visible position in August of 2026. Astronomers are already making plans for that critical observation window. The presence of a world like this inside a binary star system would fundamentally challenge our models of planetary formation. The competing gravitational forces from 2 stars so near to one another can foster a chaotic environment, a place where planets were long believed to struggle to either form or survive. If this planet is real, it has somehow managed to endure against these immense challenges. One scientist remarked that its confirmation would necessitate a deep revision of the theories explaining how planets are born, persist, and change within such dynamic stellar systems. And so, the wait endures. The data remains in archives, subject to continuous analysis and reanalysis. Countless models are run, cycling through every conceivable configuration. Does a gas giant truly orbit our closest stellar neighbor, a world that might harbor moons where life could one day arise? The universe has so far provided only an ambiguous answer, leaving us to watch, to wait, and to wonder. In the meantime, the James Webb Space Telescope continues its other vital work, searching for atmospheres around small, rocky exoplanets, including the most compelling candidate for habitability found to date. About 40 light-years from Earth, a family of 7 worlds, each roughly the size of our own, circles a dim red star. This is the TRAPPIST-1 system, a discovery that has held the astronomical community captive since it was announced in 2017. No other system yet known features so many terrestrial planets packed into such a compact arrangement. 3 of these worlds orbit within the star's habitable zone, the region where temperatures could allow liquid water to remain stable on their surfaces. Of this trio, TRAPPIST-1e has risen as the most fascinating. Its physical properties, its size, mass, and density are remarkably similar to Earth's. Furthermore, its orbital distance from its star is just right for moderate temperatures. If any planet in this system were to host an ocean, TRAPPIST-1e stands out as the prime candidate. There is, however, a critical condition. For liquid water to exist, the planet must possess an atmosphere. Without a protective blanket of gas to retain heat and stabilize its climate, any surface water would either freeze solid or dissipate into the vacuum of space. The central question, then, is whether TRAPPIST-1e has an atmosphere. The James Webb Space Telescope has been dedicated to finding an answer since it commenced its science operations. The findings thus far are tantalizing, yet they remain inconclusive. Employing its near-infrared spectrograph, astronomers carefully observed TRAPPIST-1e as it transited, or passed in front of, its host star.
This elegant technique, known to astronomers as transmission spectroscopy, works by searching for chemical fingerprints in the starlight that filters through a planet's atmosphere. If gases are present, they will absorb very specific wavelengths of light, creating telltale gaps in the resulting spectrum. The initial observations successfully eliminated a few possibilities. It was determined that TRAPPIST-1e does not have a thick, hydrogen-rich atmosphere of the kind that envelops newly formed gas giants. If such a primordial envelope ever existed, it has long since been stripped away by intense radiation from its active red dwarf star. This outcome is not entirely unexpected. Red dwarf stars are known to be violent, particularly in their youth, emitting powerful flares capable of eroding atmospheric gases over millions of years. The inner worlds of the TRAPPIST-1 system have been exposed to this stellar radiation for billions of years.
But planets like Earth can generate secondary atmospheres. Volcanic activity can pump gases from a planet's interior to the surface, and a process called outgassing can release trapped volatile compounds. Our own world, after all, lost its original atmosphere and gradually built a new one. The data from Webb contains faint hints that TRAPPIST-1 may have followed a similar path. Researchers have noted possible signatures that would be consistent with a nitrogen-heavy atmosphere, perhaps with traces of methane. A composition like this would be reminiscent of Saturn's moon Titan, a world known for its thick, hazy layers and surface liquids. The detection, however, is far from certain. The star, TRAPPIST-1, is exceptionally active, and its own surface features can contaminate the very spectra that astronomers are attempting to measure. Disentangling the faint planetary signals from this overwhelming stellar noise demands extraordinary precision and a great deal of observational data. To that end, additional observations are already on the schedule. 15 more transit measurements have been planned, with scientists hoping to accumulate enough statistical confidence to finally separate genuine atmospheric features from the background noise. If they succeed, this detection would mark a truly historic achievement, the first confirmed atmosphere on a potentially habitable world beyond our solar system. Such a world would immediately become a prime target for future observations seeking biosignatures, the chemical imprints of life itself. According to one researcher, this effort is truly testing the boundaries of what the telescope was originally engineered to achieve. The Webb telescope was conceived before the TRAPPIST-1 system was even known to exist. The fact that it can study these distant worlds at all is a powerful testament to its incredible capabilities. The search goes on. Every transit adds another layer of data, and each new analysis helps to refine our understanding. Hidden somewhere within the noise could be the evidence that transforms everything we think we know about our place in the cosmos. And as astronomers meticulously probe distant atmospheres, Webb has also unveiled something remarkable about the way stars themselves are born, revealing a cosmic alignment that validates theories physicists have held for decades. On occasion, the universe offers precisely the evidence that science has been seeking. For many years, astronomers theorized that when vast interstellar clouds collapse to form stars, the resulting objects ought to spin in similar directions. The principle of angular momentum suggests that the rotational energy within a swirling gas cloud should be conserved and distributed to the stars that emerge from it. But observing this prediction directly proved to be an immense challenge. Young stars are born shrouded in thick dust, making the orientation of their rotational axes difficult to ascertain. Confirming that multiple stars shared aligned spins required a view of something that had long remained concealed. Then, the James Webb Space Telescope captured an image of the Serpens Nebula. This stellar nursery is located approximately 1,300 light-years from Earth and is quite young by cosmic standards, at only 1 or 2 million years old. Within its dusty filaments, stars are actively forming, slowly emerging from their cocoons into the harsh light of space. When Webb's near-infrared camera focused on the nebula's northern region, astronomers saw something extraordinary. A group of protostellar outflows, which are jets of gas blasting from newborn stars, were all pointing in the same direction. Typically, these jets exhibit varied orientations, as each star should have its own random axis of rotation, with its jets aligned accordingly. Observing multiple jets slanted at the same angle suggested a deeper, more fundamental process was at play. A scientist involved in the study likened these aligned outflows to sleet pouring down during a storm, offering a frozen record of the fundamental processes behind stellar creation. As they gather mass, young stars eject supersonic jets from their poles. These jets then collide with the surrounding gas and dust, generating bright shock waves that are visible in infrared light. The orientation of a star's spin is revealed by the direction of the jets it expels. Within the Serpent's Nebula, a stellar nursery populated by exceptionally young stars, some merely 100,000 years old, a fascinating pattern emerges. The majority of these fledgling stars share a similar rotational alignment. This uniformity is a direct inheritance from the original spin of the immense cloud of gas and dust that collapsed to create them. Such a discovery carries weight far beyond confirming a principle of physics. The shared alignment of spinning stars could have profound effects on the formation and subsequent development of planetary systems. It may also influence the probability of stars forming in binary pairs. The stability of any worlds that eventually coalesce from the surrounding material might even be connected to this initial orientation. The James Webb Space Telescope has proven to be an unparalleled instrument for locating young stellar objects. One scientist remarked on its power, noting that in this area of study, they can now identify the signatures of virtually every young star, down to the very lowest mass examples. The observations within the Serpent's Nebula also brought other unexpected details to light. Delicate filaments and wisps of varying colors trace the light of protostars, still shrouded in their natal clouds, as it reflects off surrounding material. Hazy orange areas signify dust that lies between these reflections and the telescope. The resulting image presents a complete narrative of star formation as it happens. Webb has located stars at every conceivable point in their development. Some objects remain deeply encased in thick cocoons of gas and dust. Others are just starting to break free, while fully formed young systems are already clearing away their birth clouds. Each new dataset contributes to a more cohesive understanding of how these stellar nurseries function. The entire process is revealed to be more chaotic, dynamic, and varied than simpler models had once proposed. Even so, fundamental laws, such as the conservation of angular momentum, are clearly upheld. The universe operates according to a consistent set of rules, and with every image the telescope sends back, those rules become more distinct. From the Serpent's Nebula to the Carina Nebula, cosmic birthplaces across the heavens are beginning to yield their long-held secrets. One of the very first images released by the James Webb Space Telescope fundamentally altered humanity's view of the cosmos. It was a portrait of the cosmic cliffs, a vast wall of gas and dust that appeared to rise like a mountain range against a backdrop of countless stars. Concealed behind this structure, invisible to all previous observatories, was something truly remarkable: hundreds of newborn stars.
This image captures a small section of the Carina Nebula, located approximately 7,600 light-years from our own planet. What looks like a dramatic landscape of peaks and valleys is, in reality, the edge of a colossal stellar nursery. The cliff-like structure delineates the boundary between the dense gas, where stars are being born, and a cleared-out cavity, which has been sculpted by intense radiation from older, more mature stars. While earlier telescopes could perceive the cliff itself, they lacked the ability to penetrate it. Webb's capacity to see in infrared light changed everything. By peering through this dusty curtain, the telescope uncovered protostars still in the process of accumulating mass. These were objects that had never been seen before, wrapped in shrouds that absorbed visible light but permitted infrared wavelengths to pass through. Every single glowing point in the image signified a star in the midst of its formation. The view also captured the powerful jets and outflows emanating from these hidden stellar infants. These are streams of matter being ejected at incredible speeds, which then collide with the surrounding gas and create intricate patterns that trace the often violent nature of stellar birth. The cosmic cliffs, however, did more than just reveal hidden stars. They provided a stunning demonstration of the interplay between creation and destruction that propels cosmic evolution.
The intense radiation pouring from nearby mature stars is actively eroding the face of the cliff. Gas is essentially boiled away by this relentless bombardment. Over the course of millions of years, the cliff will gradually recede, exposing more of the dense gas behind it to this harsh stellar environment. As this erosion continues, it simultaneously compresses the gas along the boundary. This compression is what triggers gravitational collapse. New stars are therefore forming precisely because the cliff is being worn away. This very same dynamic is at work in the pillars of creation and innumerable other stellar nurseries throughout our galaxy. The radiation from one generation of stars becomes the catalyst for the formation of the next. In this cosmic cycle, destruction gives rise to creation. The Carina Nebula stands as one of the largest and most luminous nebulae visible in our night sky. It holds vast reservoirs of gas and dust, providing enough raw material to form thousands of stars over many millions of years. Webb's observations are now mapping this cosmic inventory with a level of detail that was previously unimaginable. The telescope has examined other regions within Carina, far beyond the cosmic cliffs. Every new observation uncovers more protostars, more outflows, and new structures that both challenge and refine our models of how stars come into being. The decision to release this image early in the mission was a strategic one. It was a powerful demonstration of the telescope's capabilities. It immediately seized the public's imagination. It served as a clear announcement that a new chapter in astronomy had officially begun. Yet, its scientific importance extends well beyond its public relations value. The data embedded within the image contain a wealth of information about stellar masses, the rates of star formation, chemical compositions, and the various stages of stellar evolution. Researchers will be analyzing these observations for many years to come, extracting insights that will illuminate the processes by which the galaxy constantly renews itself. Every star that is born will also, one day, die. Some will end their lives in supernova explosions, scattering their heavy elements across space. Others will fade more gently into white dwarfs, their outer layers drifting away to form planetary nebulae. A select few will collapse into neutron stars or black holes. But from the remnants of stellar death, new stars will eventually emerge. This cycle is continuous. It has been unfolding for billions of years,
and will persist for billions more. The cosmic cliffs offer us a glimpse of a single moment within this eternal dance. And the telescope that captured this moment continues its mission, unveiling more of the universe with each day that passes. In a span of just 3 years of scientific operations, the James Webb Space Telescope has fundamentally transformed our comprehension of the cosmos. It has called into question theories that were held for decades. It has uncovered objects that, according to previous understanding, should not exist. It has shown us a universe that is far stranger, older, and more dynamic than anyone had ever conceived. This, however, is only the start. The observatory was engineered for a minimum operational lifespan of 5 years, but it carries enough fuel to potentially extend its mission to 20 years or even longer. Provided there are no major equipment failures and the instruments remain functional, Webb could continue its observations for decades. What might it find in that time? In the immediate future, astronomers will persist in their efforts to probe the earliest galaxies, seeking out the very first stars and black holes that materialized after the Big Bang. They will chart the chemical evolution of the universe, tracing how heavy elements forged in supernovae spread to form subsequent generations of stars and planets. They will investigate the supermassive black holes that existed at cosmic dawn, putting theories about their rapid growth to the test. Hypotheses such as the heavy seeds model, the existence of black hole stars, and direct gas collapse each make specific predictions that Webb is uniquely equipped to evaluate. The enduring puzzle of the Hubble tension will also remain a focus of intense study. Is the universe expanding at a rate faster than our current models can explain? Could a force like early dark energy be the missing piece of the puzzle? One of the great questions is whether dark energy remains constant or evolves through time, and the telescope's data is helping to narrow the range of possibilities, potentially leading toward a definitive answer. In our own galactic neighborhood, Webb will persist in its study of atmospheres around distant planets. An especially compelling part of this work involves the search for biosignatures on worlds like TRAPPIST-1e. This quest stands as one of the most significant scientific endeavors humanity has ever undertaken. Discovering any sign of life elsewhere in the cosmos would fundamentally alter our perspective on our own existence. There are also potential planets, such as those at Alpha Centauri and TWA7, that await confirmation. Further observations are needed to establish if these are genuine worlds or simply illusions born from interference in the data. Should they prove to be real, they will immediately become prime candidates for detailed investigation. The telescope will also maintain its vigil over stellar nurseries, where new stars and their planetary systems are born. Every protoplanetary disk it observes offers new clues about the process by which planets coalesce from vast clouds of gas and dust. With each new dataset, our knowledge of our own cosmic origins becomes more refined. What's remarkable is that the full potential of the telescope is still being uncovered. Scientists and engineers are constantly devising new methods to operate its instruments, extending their performance far beyond what was initially designed. It is from these ongoing efforts that discoveries we cannot yet even imagine may arise. Yet, Webb does not work in isolation. The Nancy Grace Roman Space Telescope, which is planned for a 2027 launch, will enhance Webb's findings through its wide-field surveys. Meanwhile, ground-based observatories, including the extremely large telescope being built in Chile, will contribute complementary viewpoints from Earth. A new generation of astronomers is also coming of age, ready to interpret this wealth of information. Many of the students who were just children at the time of Webb's launch will dedicate their entire careers to its data, building upon the foundational knowledge we are gathering now. The inquiries that Webb pursues are timeless ones. They touch upon fundamental wonderings about our solitude in the universe, the origins of everything, and the ultimate fate of the cosmos. These are the same questions humanity has contemplated since first gazing up at the stars. For the first time in history, however, we possess the tools that can begin to provide concrete answers.
This has created a rapid acceleration in the pace of discovery. A fascinating cycle has emerged where each observation uncovers new puzzles, and each new puzzle in turn motivates further observation, propelling our understanding forward. We find ourselves in a truly remarkable era. An observatory positioned 1,000,000 miles from our planet is actively redefining our comprehension of reality. It is changing what we know about stars, galaxies, black holes, planets, and even the expansion of space itself. The universe, it turns out, is not quite as we had imagined. And perhaps that is the essential purpose of such an instrument. The most profound discoveries may be those that compel us to reconsider everything, to challenge our long-held assumptions, and to construct a new vision of the cosmos on a more solid foundation. The James Webb Space Telescope has offered us this incredible gift, and its journey of revelation is far from over.